Good morning everybody. So we begin today's session.
I just have here. Yeah.
Okay, with Janko BÖHM talking about IBP identities for Feynman integrals.
Thank you very much, and thank you for the opportunity to talk at this nice conference, at this very nice place. And what I will talk about is what computer algebra can do for your problems in physics, and in particular what new methods for massively parallel computations can do for you. So that is something which is an old thing in scientific computing and numerics, but it's a quite new thing for computer algebra. And I will describe a little bit what computer algebra can offer you there. I will talk shortly about a couple of classical problems which are also relevant, in particular for this intersection theory method. And then I will give a short outline how we apply this to IBP reduction. And Yang in the afternoon will go into more details of the physics on that topic. And time permitting, I will say a few words on another topic which actually involves intersection theory also and Feynman integrals, and is a mathematical topic from mirror symmetry. Yeah, so I'm from Kaiserslautern, and we developed this computer algebra system Singular. It's an open source system, and it's for polynomial computations. You can say for commutative algebra. And we have a lot of development teams contributing also to this system. It was founded by Gerd Martin Greuel, which you perhaps know as a long-term director of this Oberwolfach Institute, Gerhard Pfister and Hans Schönemann. The current head is Wolfram Decker. And the features include, first of all, Gröbner bases over various fields or the integers, free resolutions, computations in local rings, normalization, which is a process which improves singularities, primary decomposition, which I think this thing, does it still work? Yeah. Primary decomposition, which is a version of integer factorization, but for algebraic varieties. We have invariant theory, we have non-commutative methods if you want to compute an annihilator of an operator and stuff like that, if you want to compute with differential forms. And of course all that gets mirrored on the geometric side to algebraic geometry and also topical geometry more recently, so we can classify singularities. So if you have critical points, of course it matters what kind of structure does this critical point have, right? You can't just count the critical point. So that you can do, you can resolve singularities, you can do deformation theory, you can do sheaf cohomology, de Rham cohomology, you can do rational parameterizations as far as they exist, you can do topicalization, which is converting algebraic geometry into a kind of combinatorial version. You have some algorithms from geometric invariant theory. So there's all kinds of stuff. There's about 150 libraries nowadays. And the basis of all is methods for non-linear algebra. So you all know Gauss algorithm, you all know the Euclidean algorithm for computing a GCD. And if you combine these two ideas, you get what's called Buchberger's algorithm to compute Gröbner bases. And if you think of a GCD, of course, the main operation is division with remainder. So if you have now polynomials in more than one variable, it's of course not clear how to do division with remainder. So you have to fix what is called a monomial ordering. You can order your monomials just like you would write them in a lexicon or in different other ways. And then you can do a division, right? And say I take this polynomial divided by these two here. then I will see that the division will finish with this remainder, and that would kind of, you would think, imply that you can't write that thing as a linear combination of these two polynomials. However, you can. So the ideal generated by these two polynomials contains that polynomial, and that is a flaw of the generating system of the ideal. So the idea is actually very easy. It makes the generating system larger. You don't change the ideal. So you will just add that thing as another generator to your ideal, and if you then do the division according to this new generating system, you of course get 0. And the result is what you call a Gröbner basis. So that solves what's called the ideal membership problem. So the division with remainder gives 0 if and only if the thing you divide is in the given ideal, provided you divide by a Gröbner basis. So that is the main computational workhorse. There's other things like factorization algorithms. And these Gröbner bases can be used for a lot of stuff. You can eliminate variables. You can intersect ideals or modules. You can compute polynomial relations, syzygies, we call these. You can compute ideal quotients, saturations, and you do all that kind of birational geometry, for example, what you need for resolving singularities, as we have discussed already yesterday. That is something which is relevant to the module intersection, to the intersection theory method. If you want to know more about these algorithms, there's this book of Groll and Pfister, which is a nice reference. You can also try Singular out online. So you can just go to the web page and see here some example sessions. So Singular will also be available soon as a cornerstone of a new open source computer algebra system called OSCAR, which is developed in our transregional Sonderforschungsbereich. And so that combines Singular with other open source systems for number theory, group theory, and polyhedral geometry. And the unifying language is a new language called Julia, rather recent language, which has a lot of nice features. For example, it can do just-in-time compilation of code. So let me discuss a little bit this resolution of singularities. So this was a big result by Hironaka. He got a Fields Medal. And yeah, so if you look into his proof, he uses what is called a so-called order sequence. So this is a sequence of vanishing orders of a Gröbner basis, but in a local setting, a standard basis. And he proved the existence of resolution of singularities in characteristic 0. In characteristic P, it's still an open problem. And so if you look at this criterion, of course you have to check it at every point, right? And there are infinitely many points, but you can easily turn this into an effective criterion, for example, to test smoothness in the first place, but also then to resolve singularities. And what happens there is that you work with the Zariski topology, so you look at complements of 0 sets of algebraic equations that are your open sets. And then you iteratively go to smaller open sets, and you get a covering in form of a tree of charts. And here you see already parallelism coming into the game, right? Because there are a lot of leaves usually in such a tree of charts. So we developed a smoothness test based on that idea and based on algorithmic versions of resolution of singularities, which I will discuss in a second a bit. And yeah, so that writes actually every smooth variety as a locally as a smooth complete intersections. So for example, if you take these three equations, they define a curve in projective 3 space. So it's one equation too much, right? More than you would expect. But if you go to an appropriate open subset, it's a complete intersection of 2 equations, and you see the 2 hypersurfaces, and the curve is this black thing, right? So if you project this curve to some directions, then you will see that you obtain singularities, and there's an inverse process called blow up, which will replace this point by a line and then allows to resolve singularities. Here we still have an exceptional divisor which is tangent to this curve, so we will have to blow up further to get normal crossing. And that all has been made algorithmic, this Hironaka method, by a lot of different people, in particular Bravo and Sinas Villamayor. This is what's implemented in Singular and was implemented by Frübis, Krüger, and Pfister. If you look at higher dimensional problems, you see that, of course, things become much more complicated. So you have lines of singularities which again meet in points, and you have to think very carefully what to blow up to get a resolution of singularities. And again, you get such a tree of charts, and that, of course, leads to the idea that one should traverse such a tree in a parallel way. And to draw information of that tree, of this tree of charts, you again need kind of a parallel algorithm which traverses this tree and draws some information from it. For example, the intersection matrix of the exceptional divisors or whatever you're interested in. So that got us started to look at massively parallel methods, because you can get an awful lot of charts. And yeah, so this goes with the smoothness test into a couple of hundred in usual examples. And luckily in Kaiserslautern there's this Fraunhofer Institute for Industrial Mathematics, and they have already a ready-made workflow management system for massively parallel computations, and that we combined with Singular. So Singular calls the system calls many singulars. This is kind of the basic idea. And this system contains out of a distributed runtime system, so it assigns tasks to workers. And it is more than that. It is also a programming environment and separates the computation from the actual coordination of the algorithm. So you can formulate your algorithm in a nice environment, and for that we have a specialized language which is a so-called PetriNet. And in the computation layer, on the other hand, you can use, say, singular procedures, but you could call anything which is callable as a C library. So these PetriNet, they were introduced by Carl Adam Petri as a graphical way to describe concurrent asynchronous systems. Yeah, I guess the world is such a thing also, right? And mathematically, it's a bipartite directed graph. It has places and transitions. The places can contain tokens which you want to work on. The transitions consume tokens, produce new tokens. This is the basic idea. And the transition can fire if all input places of a transition have a token. So here's an example. Here's a token on a place. Here's a transition. Here's another place. The light is off. This is a drawing of Petri, or by Petri, not of Petri. It's of his son. Petri was not better computer scientist than artist. So here's this token. The token gets consumed by the transition. The token is here. Now the light is on. This is kind of the very basic idea. This transition can fire because here are tokens. You get to this here. This cannot fire because here is a token missing. All right? Here's my favorite example of a real-world PetriNet. We have someone who wants to shoot someone else. So we have here's the assassin. So here is a token, and so the assassin has to load the guns, and the gun is loaded. So there will be a token here. The assassin pulls the trigger, fire pin is struck. You can get a misfire, or the gun fires. So this is a randomized way to execute such a Petri net. This could fire or that. So the guy could be lucky or not, right? So you have to take that into account in your algorithm. It's always a randomized algorithm. Someone could unload the gun, the victim is shot, then the victim dies. Yeah. So the main feature of these Petri nets is parallelism. So you can have both transitions which can fire in parallel if here are tokens. But what you can also do, and which is in some sense more important, if you have several tokens on such a place, you can execute the transition several times at the same time without any problems in your algorithm, if you have formulated the algorithm as a Petri net. In the real world, of course, it's a little bit more complicated. Transitions take time in the real world. The tokens are not just there or not. They actually can contain data, and the transitions can actually be picky and say, I only want tokens of the following kind. But that makes the programming much easier. So we have looked so far at a couple of examples of applications. So from classical algebraic geometry, we implemented the smoothness test based on this Hironaka idea, resolution of singularities, which can handle then much bigger problems than what the current implementation, sequential implementation in singular can do. We did some algorithms from geometric invariance theory. We did tropicalization, so converting an algebraic variety in this combinatorial shadow of it. And we did integration by parts reduction. And we also applied it to another topic which arises from mirror symmetry, is connected to algebraic geometry, tropical geometry, and string theory. So this is about generating series and recursions for Gromov-Witten invariance. Yeah, so let's quickly go back and think a little bit about this classical application. So parallelism in algebraic geometry, we said, comes from the use of charts. This is one source of parallelism, and it kind of mirrors the idea to describe schemes in terms of charts and glue these charts together to get a more complicated object, and this idea of sheaves and vector bundles and so forth. And then, of course, you want to relate global properties to local properties in the charts, and this is a non-trivial problem. If you want to use this parallel structure on a computer, you think in the first place, and this is why people didn't do it for long, that it's not really possible. And the problem is that a single chart may dominate your runtime, because in every chart you will somehow run this Buchberger algorithm, and Buchberger algorithm is worst case doubly exponential, so it's not a very predictable algorithm. In many examples it's very fast. So Meyer and Meyer showed that it's double exponential, and what we observed is now that if you give the algorithm the choice of the chart, you actually can get a very good algorithm out of this approach, because, I mean, a given algebraic variety has a lot of covers by sets of charts, a lot of atlases. So if the algorithm can choose from a large set of charts and, say, test smoothness in a given chart, and finish once it has covered the whole variety, then of course the fast charts will win if you have, say, a cluster with 1,000 cores and you have not more than 1,000 charts, right? And even if there are more charts, it will also work in a very nice manner. So that actually leads to a very strange thing. If you double your computational resources, you get a speed up which is much more than double. And the reason is that some computations usually would get stuck. So here's something for a so-called numerical Godot surface. It's a general type surface, codimension 11, which was constructed by Schreier and Stenger. And the usual Jacobi criterion, which looks at minus of the Jacobian matrix to test smoothness, is completely infeasible there. But this chart approach works, and you see this is seconds, so you can certify smoothness in less than an hour if you use enough cores. And you see, say here, you double the resources, but the speed up is much more than double. And that we see in a lot of problems, actually, that the algorithm can, in a massively parallel way, find the way to the answer better if you kind of give it the freedom to do that. So let me come to the integrations by parts reduction. So, I mean, the setup we have seen now a couple of times. We have some Feynman diagram, we have some Feynman integral. The variables are connected through impulse conservation. We have some external variables, some internal variables. We go to the Spikov representation, and then we have a couple of external parameters for this graph here. It's 5, and then we have various integrations to do, and yeah, now you can basically write any integral as a linear combination of integrals of this monomial type. And of course, there's an awful lot of monomials, so we want to have these integration by parts identities to relate these integrals. So as we have also seen a couple of times, you do such a total derivative and get these identities. And what we do now is we impose some more conditions to get only physically relevant integration by parts identities. So we want to avoid shifts in the dimension parameter, and we want to retain that these exponents are less or equal than 0. So that translates into such an equation, which in algebraic geometry is known as a syzygy equation. So this is a syzygy between partial derivatives of the Spikov polynomial, modulo the polynomial, and it translates in such equations. And if you have now such a integration by parts identity, it's such a vector of A's, and first of all, the two conditions separately are relatively easy to handle. So we have shown that in this paper that the syzygy equation can be solved by Laplace expansion. And so we know this condition here, and it's a module membership. Remember, it's like this ideal membership I talked about at the beginning. And the second condition you can also easily formulate as a module membership. And now you want to satisfy both conditions, so you intersect these two modules, compute up to a certain degree. So this is the use of nonlinear algebra for this IBP problem via Gröbner basis, because this intersection is computed using Gröbner basis. And then if we write down the possible IBPs up to a certain bound, then we need a reduction algorithm. So we do a semi-numeric reduction, so we replace some of the parameters by constants, and Yang will talk more about that stuff, so I will just quickly go over that. And then we interpolate the parameters which we replaced by numbers. So we could, for example, handle this non-planar hexagon box with this approach. But of course what you see is you need massively parallel methods, and for this computation we did it more or less by hand on the cluster. For this non-planar double pentagon thing, we then use this GPI space approach, which makes life much more easy and speeds up matters very much. So just to give you an idea how this corresponding Petri net executed by GPI space using singular looks like, this is such a, basically the reduction and interpolation step. So we do a full pivoting, we find the degrees of the respective variables by univariate reduction, symbolic univariate reduction, and we dynamically replace bad points in the reduction. We have here a so-called interpolation tree data structure which controls the state of the interpolation, and the leaves of that tree are essentially the final results. So we fill out this tree iteratively, and if we have a sufficient number of interpolation points, then we trigger the next interpolation of the next variable. So that you can find in this paper. To give you an idea how that thing scales, here is the number of cores we use for, so this is for one of the 11 cuts. The easiest actually, because otherwise you can't analyze the scaling because it won't finish on one core, right? So, and you see the speed up keeps up quite well with the number of cores. And if you divide by the number of cores, you get what's called the parallel efficiency, and this is in a very good range for parallel algorithms. If you start out here with the parallel efficiency, you can actually compute a kind of theoretical idea how much percentage of your algorithm is parallel, how much is sequential. And this is this purple curve here, and you see the actual speed up keeps very well with this parallel efficiency, which you would theoretically expect. So that is the easiest of these cuts. Finishes in 10 minutes on 384 cores. They are more difficult ones that take in the range of hours. So you can, if you use enough cores, you can finish this computation in a day or two. Yeah, and this involves interpolation up to degrees, something like 35 in that range. So how much time do I have left? Question to the
10 minutes.
10 minutes. Okay, so I can say a little bit something about the other topic we are working on, which involves Feynman integrals, and I think also is related to this intersection theory question. So this comes from mirror symmetry, which looks at so-called Calabi-Yau varieties. So one-dimensional Calabi-Yau is an elliptic curve. You have seen these for sure. And then there is this famous quintic and projective force space. And then people are interested in a mirror construction. So you have to Calabi-Yau, you have a mirror. And to both of them, you can associate what's called the A and the B model. And the A model are so-called Gromov-Witten invariants, and these are intersection numbers on the modular space of stable maps of certain genus through a number of points of a certain degree. So think of, say, curves in the plane through a given number of points of a certain degree, something like that. But now not in the plane, but in the Calabi-Yau. And the B model arises through Feynman integrals. And this side is very well understood. The mirror constructions come from physics and also from mathematics. The string theory picture is also very well understood. This here is understood in terms of algebraic and symplectic geometry by these people. Here, it's not so totally clear what is going on here on this Feynman integral side. And the first mirror theorem was by Giventhal and Liu and Yao. So this was for this quintic hypersurface, and it's for genus 0. So genus is the number of loops in the graph, right? So what you get is a generating series which encodes certain Gromov-Witten invariants, which actually you can interpret as numbers of lines and conics and cubics and so forth on your Calabi-Yau variety. So it is very geometric idea, and the algebraic geometry people computed these numbers, but they had a couple of them they had wrong, so the physicists told them, listen here, something doesn't fit really with our idea. So they fixed it. And I mean, there are some theorems on higher genus problems. And the question is, of course, can you produce mirror theorems for arbitrary genus? So arbitrary loop order. And can you understand the mirror theorem beyond just a combinatorial identity of numbers? And of course, what are these B-model integrals actually? So we said, okay, we are not so ambitious, so we started out with elliptic curves. This is the easiest Calabi-Yau. And here, in fact, the Gromov-Witten invariants have a very nice interpretation. They are Hurwitz numbers, so this is a weighted, these Gromov-Witten invariants are a weighted number of degree d covers of the elliptic curve by some other curve of a certain genus with a certain number of ramification points according to this Riemann-Hurwitz formula. Of course, genus 0 is not an option here because there are no such maps from a genus 0 curve to an elliptic curve, which is a genus 1 curve. So we had to look at higher genus. And to understand that, we passed through this tropical geometry. So this is this combinatorial version of algebraic geometry, which essentially, if you think of an elliptic curve, this is, in the differential point of view, it's just a torus, right? And what you do is you shrink that to a circle in tropical geometry. So a tropical elliptic curve is just a circle. And then you can take a detour, or rather probably a shortcut through tropical geometry. So you have also tropical Gromov-Witten invariants. You have a correspondence theorem which tells you that these two kinds of invariants are equal. And these B-model integrals, they relate very nicely to the tropical picture. So this whole idea goes back to Gross and Siebert. So Mark Gross had a result for P2, which you can think of as a building block of a Calabi-Yau. So you can piece together a Calabi-Yau surface out of several P2s. But the piecing together is still kind of a mystery in many situations. And so we refined this whole idea a little bit for this elliptic curve by making a finer version of mirror symmetry, which implies the mirror symmetry you are interested in. And we also extended it further. So in general, a Feynman graph for us is a 3-valent connected graph of a given genus. And we have extended this now for higher valencies and also for genus at the vertices of the graph. So you can think in a point on this graph there's a substructure. Yeah, so this is such an example. So there are no external legs, right, in our picture. And then on the Feynman integral side, we also have a propagator, which is a Weierstrass P function. We assign this propagator. So how much minutes are left? 5. Good. Yeah, that's good. So we have this propagator, which is a Weierstrass P function. This is 1 over z squared, but then you must make it periodic on your elliptic curve, which is a torus. So you can think of it as C modulo lattice. And yeah, so the integration then happens through parallel paths on this torus. So you identify that, and that, and that, and you get a torus, and there are your integration paths. the integration variables are, in our settings, the vertices of the Feynman graph. And then we have these tropical Hurwitz numbers, which is this tropical analog of the classical Hurwitz numbers. Without going into much detail, if you have such a tropical cover, it comes with a certain multiplicity, so you have to count these covers with this multiplicity. And the cover is essentially a metric map between graphs. So the graphs have lengths on the edges, and if you normalize the length in the target to 1, you see that you can encode everything in weights of the edges. So if you want to count these covers now, then this is kind of a little bit of a problem, because you always miss something. And there the Feynman integrals come into the game. So the first thing we proved is that actually these invariants, the classical and the tropical ones, agree by actually a correspondence of covers. So from a tropical cover you can make an algebraic cover. The map is kind of inclusion reversing, so the components here are the vertices here, and the edges tell you how the components intersect on the algebraic side. And if you want to compute that stuff now, say you want genus 3, degree 3 maps to your elliptic curve, then you see you have two graphs which can contribute. Graphs with bridges can't contribute, they give 0, you can show that. Then you see, okay, I can count this, and I add it up with these multiplicities, and I get this number, it's 160. Yeah, but you always forget something. So it's nice that you can compute actually not only the number, but actually the cover from the Feynman integral. So we take this product of propagators, just as done in physics, and we do this integration, and then essentially we evaluate the integral by residue computation. And so we look at a certain coefficient in a power series expansion of our product of propagators. In fact, of course, these are generating series of propagators in some sense, so there's a formal power series variable, and we have one for each edge. And if you put all these q's to one single q, you get this classical result back. So we have this more refined version where you have this multivariate setting in the q's, and you fix not the degree, but how often the edges come over a base point with which multiplicities, and then we get this refined version of mirror symmetry, which implies the one which was already known for the elliptic curve by a work of de Graaf. Yeah, so to compute the Feynman integrals, you write down your propagators in a right coordinate system. This generating series of propagators looks like that. So you can look at the respective coefficients of this q. This a is counting these multiplicities of these edges, so to say the degree. And then you can evaluate these tropical Hurwitz numbers just by looking at constant coefficients in the product of propagators. In fact, these generating series, one can show, are quasi-modular, so you can write them as an element in the algebra generated by these Eisenstein series E2, E4, E6, and they are of uniform weight, of a certain weight, depending on the degree, on the genus of the graph. And yeah, for example, for that graph, you will see that this generating series is of weight 12. So it can be written in these monomials. So what we do is, with our massively parallel method, we compute this generating series to high enough order. Then we solve a linear system of equations to write the generating series in terms of the Eisenstein series. And then you can compute that thing to arbitrary high order. Yeah, because you have kind of a recursion for your coefficients. Yeah, you just evaluate this element. Okay, that's what I wanted to tell. I think I should be in time.
Yes, you are.
Thank you.
questions for Jan?
Does the computation of parametric annihilators also parallelize the for the computation of parametric annihilators, does this also parallelize in an efficient way?
So this is a non-commutative computation, right?
Yeah.
So there's no parallelism for that yet. I mean, there's also no parallelism for the Buchberger algorithm yet, except if you use linear algebra methods. But of course, if the individual computation finishes and you want to do a lot of them, you can do that in parallel, right? But I mean, this is something we are thinking about because it, of course, appears in a lot of problems that you want to also solve these nonlinear systems of equations in the end in a parallel way, because at some point the individual computation becomes the bottleneck, especially if you do non-commutative computations, which tend to be very complicated.
Yes.
I may have missed the point, but thank you for your nice talk. I was wondering whether can you use any alternative of integration by parts identities or tropical integration by parts identities in this set of calculation? Have you?
So you mean in the second topic I talked about? This is exactly a question which I have for you, because of course I was thinking about how do these two things relate, right? I don't really understand how these two things relate. The second thing is clearly related to intersection theory in some way on these moduli spaces. And there should also be some integration by parts identities and stuff like that. It can be that the example is simply still too simple, that you can see something really, really meaningful. But I mean, it's a multivariate integration. It's for arbitrary genus, so there should be something to see, but I don't know. Okay. That's why I talked about it, because I hope for someone saying, I understand something there.
Thank you. Thank you very much.
No more questions for Jan?
I have one.
Oh, yes.
Is this one even on? Yeah, okay. So you had this syzygy equation on one of your slides.
Mm-hmm.
So if you can maybe go to it.
Yep.
Something is broken in your page counting.
Yeah. Yeah, I wasn't sure whether we get to the second part depending on how many questions there are. So I would have skipped it.
Syzygy equation.
Where is the syzygy? Here.
Yeah, that one.
That thing.
Exactly.
Yeah.
Okay, so we agree that A and B are the unknowns, so to speak, unknown functions.
Yes.
And what you can do is to find expressions for A and B that makes this equation true.
Exactly.
Okay.
So you can just use Schreier's algorithm for computing syzygies.
What you should have done if that derivative, which is now working on P, which is known, so it's easy, if that instead have been working on your unknown, like on one of the A's, could you still have had, I mean, then it's no longer a syzygy equation in the standard form.
No.
But can your code still help with that kind of stuff?
I'm not sure whether what one can do then. One would have to see the explicit problem. So if you can show me.
If you don't know this P, try to solve this P.
Sorry.
I guess your question is, suppose there's an inverse question. So the thing is, suppose you know this kind of A, you try to find this P, isn't it? Is that a question?
Is that the question?
No.
No, I don't think so.
But I was thinking about P would still be known initially, but you just, I mean, maybe you had some combination of A's on some terms and derivative of the same A's on other terms.
But here we only have the derivative. You mean to add some?
I can write down an example.
Oh, okay, okay.
I mean, I understand what you mean. So you mean you have some, I mean, this is a kind of a kernel of the vector of partial derivatives, right? This is what it is. Okay, we compute modulo P, but this is the kernel in a quotient ring. right? And if you know the A's, we know the B's. So what you ask now is basically, you have some more components which are unknown in some sense, right? So that gives you, of course, more freedom. I would say probably too much freedom, right? Then you could do anything in these components. So I'm not sure whether I understand what is the questions. We probably have to have a look later. Yeah.
If there are no more questions, let's thank Janko.
Next. So next speaker is Yoshida. Where is it?
Yes.
Troppo vicino alla bocca. Talking about the Schwarz map for the hypergeometric function. Please.
Blackboard or slides?
Oh, also, I use Blackboard. Oh, okay. I don't know how it works.
So you press this, so it goes. Yeah.
It's next.
Yeah, and this is the laser pointer.
Good morning. Thank you for the organizer. This is a symposium for physics, and for me it's the first time to speak in symposium in physics. But since my physics is still in undergraduate level, I speak only mathematics. Sorry. And also, I'm not good at abstract modern mathematics, so my speech is in a very elementary level. So I start. So my topic is hypergeometric function, and I want to tell you how I love this differential equation. Maybe there's no need to explain. This is a hypergeometric differential equation. I hope everybody knows. And this is one Euler integral representation. So it's by Euler and Gauss, so it's very long ago. You know. Anyhow, the important thing is, so 1, 2, 3 linear form with the exponent, and we make that infinity. So it is sometimes called 2, 3, 2, 4. 2, 4 means 2 means P1, 2 minus 1 is P1, and 4 means 4 including ad infinity. So in this you can see 3 terms, and fifth is ad infinity on P1. And it is not single valued. And how it is not single valued, it is very easy. I have singularity 0 and 1, and here x, and I integrate in this way. So if I let x turn around, then you can easily compute what happened. You know? So it becomes, yeah. So this part you add this part and this part. So it is very easy. Anyway, before going further, I defined Schwarz map. It is defined in end of the last century. Again, it's a very old story. And I give an typical example. So I have X space here. So singularity 0 and 1. And when ABC are real, then I can draw the image by the Schwarz map. It is bounded by part of the circle, and I know also the angle. So if it is this angle is 0, which means it when it touches, yes. So E 1/2, 1/2, 1. It's a famous example. Then it touches, and by Schwarz reflection principle. And so in every textbook, undergraduate textbook, you find Schwarz reflection principle. So you get this one, and you continue, and then you get the weapon of International Mathematical Society. Yeah, so it's a very famous one. Everybody should know. So you're a physicist, so I don't know about that. Anyway, it's a very famous one. Okay. But anyway, it is not single valued, but how it changes, it's very easy to compute, and it's here. So U1, U2 changes to U0, U1, and this is 2 by 2 matrix, and it is called a circuit matrix. And if you turn this one and this one, only 2 generate everything. So it is a generator. Very easy. And as you know, you turn around, then only a scalar multiplication, e to the power something. So the entries are just polynomial of e to the power 2 pi ia and etc. So it is very easy, undergraduate mathematics. And it is so easy, so you can easily find a Hermitian matrix which does not change under this monodromy group action. Since it is 2 by 2, it is quite easy to have H. And it is classically known, of course. And H determines the image of my Schwarz map. Okay. And this is well known more than 100 years. So there is no need to ask why H exists, because we have explicit generator and easy to compute H. So there's no need to ask why it existed for 100 years. And now, about 30 years ago, I got interested in a bit generalized hypergeometric equation, which is called Almato-Gelfand hypergeometric equation, which Almato doesn't like to be called Almato-geometry, but anyway, it is so called. So I don't write the equation. The important thing is it is in 4 variables, and the rank means a dimension of the solution is 6. And the important thing is this integral representation. Yeah, linear form, 5 linear forms, and 2-dimensional integration. So it is often written 3, 6. 3, 6 means, so if I make it homogeneous, then it is 2 plus 1 is 3, and 5 lines, and line at infinity is 6. So it is often called 3, 6. Anyway, it is written in this way. And why I and so from now on, I often say we. We means I and my collaborators. We are interested in the special case where A1, A6 are all 1/2. And when it is 1/2, this is, if I write in this way, then it is all 1/2. So in this case, it's a very direct generalization, 3, 6 to 1/2. And it has an algebro-geometric meaning, and in this case, inverse function, inverse map is a famous automorphic function called lambda. And in this case also we have this kind of automorphic functions, and it is, for us it is interesting, but it is not a subject today, so I skip it. Anyway, we thought for general A1 and A6, can we have still this invariant Hermitian form? This was our question. So you see, in one-dimensional case, 0, 1, and x, I go near to 1 and turn and back. I go near to 0 and come back. So this change is a circular matrix generating the monodromy group. In two-dimensional case, what we should do is, so 3 minus 1 is 2, so it is P2. 1 is at infinity, and 1, 2, 3, 4, 5, and I count, it should be 6. 1, 2, 3, 1, 2, 3, 4, 5, 6, yeah. So 6. Yeah. And what I should do is to move this and make it one triangle very small and turn around. Yeah? So in one-dimensional case, my go near and this interval becomes very small and I turn. Yeah? In two-dimensional case, I move this and make this triangle very small and turn. And it is not so difficult, but very complicated. So this kind of computation, I'm not so good. So I asked my junior friend Matsumoto to do it. But there are many such. Yeah? So generator, in this case 2, but in this case 20. So you must be patient. Yeah? So, and ask whether this H exists. Yeah? But if you know personal computer 30 years ago. So we could use machine only to check the manual computation. So 30 years ago, it was very elementary. And so another friend of mine who is good at manipulating a computer made this computation. So 20 such and find 6 by 6 matrix. Yeah. It's not difficult to mathematics, but it's a huge computation. But the answer was surprisingly simple. So we thought, there must be some reason to exist. And it took me 2 or 3 years. But when I was taking vacation in Isola d'Elba, so it's a small island near Pisa, I got an idea. If I can evaluate intersection number, so I 1, 2, 3, 4, 5. So this is the D. Yeah, so D1 indeed. If I can evaluate the intersection number of these 6 domains, then so if I can evaluate this, so it's this kind of things. If I can evaluate, then it's a topological thing. So it is invariant under small change, small change, small change. Then it is invariant under monodromy group, of course. So it is just obvious that this holds. And what I wanted to find is this one. Yeah? So I found it is just an inverse matrix. So it took such a long computation, and if I can evaluate this, it's just an inverse. And this audience, you know how to evaluate. So since I found in a poster of the symposium picture like this. Yeah. So and this is our starting point. Just easy. I compute this part and this part and this part and just sum. And in two-dimensional case, it's not so difficult. So in a few minutes, I can make it. Then we don't need this stupid long computation. So we are very happy. We means I and my collaborators. But surprisingly, among mathematicians, it was not popular at all. Still, many friends of mine ask, intersection number for twisted cycles, what for? So my collaborators knew It is important. It's very useful. But most mathematicians never estimated possibly. So when I got an email from Sebastian Mizera two years ago that this is useful for quantum field theory, I don't know what quantum field theory means, I was very surprised and happy. Yeah, our theory can be used, so it is useful. Thank you. So we made this kind of things mathematically just for fun, and many years later it turned out it is useful. It's a nice theory, nice story. Now it is 30 years ago, so let's come a bit nearer. No. Recall, yeah, so again, thank you, Sebastian. So, this is the second subject, Schwarz map, last century. But I learned this, I knew this when I was a student. Oh, so it's nearly almost half century ago, so it's an old story. But I felt the target P1 is not wrong, but it is not correct, very correct, because the monodromy group of the classical Gauss hypergeometric function is general linear 2C. So 2 by 2 regular matrix. And this group acts on P1, of course, but P1 is not a natural place for this group to act. P1 is sometimes called Riemann sphere. It's a sphere. So it's a scheme of the orange. I love inside. So for years I dreamed to find a correct Schwarz map having ball as a target. So sorry, I broke it. It works? Still it works. No. And before I find this correct one, I already named it hyperbolic Schwarz map. It is my Schwarz map, correct Schwarz map. And well, about now 20 years ago, I got an idea. Once found it is very simple and very natural. As so it is written. Riemann sphere is a sphere. It's a scheme of the orange. So I need a map into the ball. Yeah? So it should be called a hyperbolic Schwarz map. And how it is made? First, I rewrite the original hypergeometric equation to this form. It is not my original. It is already done by Schwarz. And this part is called Schwarzian derivative. So again, it is a very old story. And I rewrite this very simple differential equation in matrix form. Yeah? It's again an undergraduate mathematics. And what I did next, this is, so this is a fundamental solution, and I've only take this product. So star means transpose complex conjugate. Then it becomes a positive Hermitian. Positive Hermitian is hyperbolic. So if you divide it out by positive multiplicative positive number, then it is a hyperbolic space, and the boundary is P1. It's a complex P1, and inside the ball is one model of the hyperbolic 3 space. So I got it. This is my answer. And I want to show how nice it is. So monodromy group just act very naturally. So I have what? I have this W, and the monodromy group acts in this way. So it's just positive Hermitian to positive Hermitian. So monodromy group act just naturally. So it's a kind of lift to the air. So the classical Schwarz map has image on the surface, in the skin of the orange, but my Schwarz map has image in the ball. So it's a surface. So you see. So I have now a ball, and the skin is P1, and in the inside I identify Hermitian form, positive definite 2 by 2 Hermitian form divided by positive number. Then my image is inside, and it has a nice property. How nice? I'll explain. Well, our hypergeometric differential equation has singularity at 0, 1, and infinity, but my map has more singularity. 0, 1, and very often in this shape. So my equation is now, and this is, this curve is defined absolute value of q equals 1. And my Schwarz map has singularity here. To have singularity is very welcome, because a singular point is by definition a point which carries more invariance, more information than ordinary point. So to have singularity is a very good thing. And second, what is the relation between the old original Schwarz map and my Schwarz map? It is, so my Schwarz map is written in a big S. So here, my Schwarz map image, and I take normal here and extended geodesics. Then it hits the ideal boundary. This is the original Schwarz map. And there's other, and this is, I defined, it's a derived Schwarz map, Schwarz image. The derived one is defined by very simple derivative. Yeah, so this is my derived Schwarz map. So it hit the ideal boundary at the derived Schwarz map and the original Schwarz map. So you remember my U is so this part is original Schwarz map, and this part is my derived Schwarz map, and altogether it's my hyperbolic Schwarz map. So it's quite natural. And in original Schwarz map, almost always the image becomes chaos. So when the monodromy group is a nice group, for example, this kind of things, yeah, it's a nice group, but the image of the Schwarz map is just chaos. But my Schwarz map is a closed surface. If it is discrete, the image is a closed surface. So you don't need to assume ABC real, or I can make confluence up to Early function. So I want to show you the how nice it is. So in this case, is lambda function case. It goes like that. Yeah. But it is very planar. But by Schwarz map, my hyperbolic Schwarz map image is like that. So it is in the ball, so it is infinitely many things. I forgot to tell you that generically the image of this one becomes this shape. This shape means cuspidal edge, and this part swallowtail, if you know. So, and I want to show you another nice example, not infinitely many. So dihedral Mondolmi group, then more easy to, yeah. So this is the dihedral case, the planar images, just this one, nothing interesting. So this is, but my hyperbolic Schwarz map, this nice shape. This is my Schwarz map. Yeah, I love it. Many mathematicians asked, what is the application? I don't care. I love it. It's enough. So it is different from a physicist. We mathematicians, we just do what do we want and just enjoy. I love it. Thank you.
Well, very good. Okay, so let's thank Professor Yoshida for this very nice talk. Are there any questions? Many questions.
So I would like to tell you something inside the orange that may make you happy. You've heard us talk about Feynman integrals, yes? And they're classified by the number of loops. Every one loop Feynman integral is the volume of a simplex inside your orange in hyperbolic 3 space.
Thank you.
To understand this, I want to understand this a bit better. So you said that when the monodromy is discrete, you get a hyperbolic 3 manifold. You get you had the example, you get a Bianchi manifold.
Yeah.
And your surface S, is that a geodesic inside this?
What?
Is your surface S a geodesic surface inside this 3 manifold?
Geodesic?
Yes, what is S? So if you have a hyperbolic 3 manifold, is S a geodesic surface?
Geodesics? I've never thought about it. No.
Okay.
I knew...
So what's the relation between S and your discrete subgroup of PSL2C?
Yeah, it's a
group of
monodromy.
hyperbolic. Yes. So what is, how does S, so you get that acts on hyperbolic 3 space and defines a hyperbolic 3 manifold.
Yeah, so
how does the surface S relate? Does it sit inside?
The image of this one is like that. Only one swallow tail. Yeah. So.
It has singularities.
And if you continue analytic continuation, then you have many swallow tails. And in this Mondolini finite case, it is like that. So this part is the image of the upper half space. And I don't know whether this is geodesic or not, but what I know is it has singularities, but still this kind of singularity, the normal is well defined. This kind of special.
That was my second question. The normal is always well defined.
Yeah. Okay.
Any more questions? So let me just make a final comment. Just don't go to Isola d'Elba just for inspiration. Remember that also Napoleon went to Isola d'Elba on holiday and got a different inspiration. So, so now we have a break until. Let's thank Professor Yoshida.
So the coffee break is served at the ground floor, and then we have to cross to the left courtyard and follow the arrows. I hope you will manage to find the place. But maybe you can take a jacket. We have to go a little bit outside, so in case you can take the jacket with you. And here we will lock the room. So we reconvene at 11.
Sarebbe 5 minuti, giusto per dire una cosa così storica. Pierpaolo, che devo fare? Devo farlo. Sono
03. Iniziamo poi.
Okay. So we continue with MANDAL from here, from University of Padova, talking about the applications of intersection theory to Feynman integrals in the multivariate case. Please.
Thank you. So as I will be talking about application of intersection theory to Feynman integrals. As Hjalte has pointed out, it's kind of the second part of where he left. So this I will be talking about multivariate case, where Hjalte showed the results for univariate case and how we can do it. So just to tell that it started with when the connection of intersection theory and Feynman integral happened, when Pierpaolo and Sebastian reported these results, that when they found out the linear relations between Feynman integrals can be obtained by simple projections, and where they can define a scalar product which is nothing but intersection numbers. And then we extended to many applications through Feynman integrals on maximally cut Feynman integrals, which have unifold representations, and checked this idea extensively, as well as for differential equations, also dimensional recurrence relations. And very recently we reported this paper where we showed that a full decomposition of the Feynman integral to all of its masters, the full, not on the maximal cut, the full decomposition of Feynman integral can be obtained where we used multivariate intersection numbers. So I will show you I will start with just reminding us again that what we are doing a bit, and then quickly go to the multivariate case. So the integrals, what we are interested, we are hearing it again and again, that the integral is just we want integral of u phi, u times phi, where u is the multi-valued function and phi is the single valued differential form, and also u vanishes on the boundary. And in the cases where we have studied here in the Feynman integral, we specifically use Bikov representation where it is automatically satisfied. And this phi is basically a representative of this two-state co-cycle, and this also in the mathematics literature one can tell as two-state cycle. And then thanks to Aomoto, Kita, and also all other Japanese mathematicians, that this integral was understood as the pairing between this cycle and the co-cycle, and and at the same time one can define with a dual of this two-state co-cycle and also a dual of the two-state cycle, and which I show you in this a cartoon here, where I define that there is a two-state cohomology group, and phi L is the representative of this group, which is the two-state co-cycle. Similarly, one can have a dual two-state cohomology group, and I say phi R is a representative of this dual cohomology group, and their pairing is the intersection number. Similarly, one can also pair between the two-state co-cycle and the cycle to get the integral, and also one can define intersection number between the cycles and also between cycle and dual cycle and dual form to define a dual integral. And all of them are related by this Riemann two-state period relation, which Pierpaolo also mentioned in his first yesterday's talk, that also this can was found out by Cho and Matsumoto, and this can help to find quadratic relations between integrals, which probably also Stefano will touch upon tomorrow on these quadratic relations. However, in my talk I will be mostly talking about this part, the integral and the intersection number between twisted forms. So I just remind you again that our algorithm for this decomposition, which Hjalte showed yesterday, that thinking about univariate case, so that we have an integral where with is again u phi, which is basically the pairing of phi and c. Only thing is that u is a function of single variable z, and phi is also a single variable of z. And then we determine the number of masters, and we know that number of master is the dimension of this two-state cohomology group, and which can be also shown to that boils down to the number of solutions of omega equal to 0. And once we know the number of master integrals, then any integral in that space can be written as a linear combination of master integrals, and where master integral can be represented as the pairing between the contour and master forms in that cohomology group. So you can see like that as the C remains constant, if, in the cases of Feynman integrals, what we are looking for, as Sebastian also pointed out, that we do not play with the C, we just go for the one row. So basically one can look, what we are looking for, the decomposition of two-state forms, in any two-state form in terms of the master forms. So then you choose basis, and in case of choice of basis, you can use monomial or D-log basis. And once you have the base forms, then you can define the metric matrix, which is nothing but the pairing between these two basis forms. And then what yesterday you have seen it also, that this is our master decomposition formula, which tells that any two-state form can be decomposed in terms of the master forms having this coefficient. But now here, if I pair it with the contour C, then I get the integral I here, and here the master integrals. So then we can quickly identify the Ci, which was my goal to determine them by this quantity. And this is the entries of this are nothing but some intersection numbers combination. And as I said that these are all univariate, so this boils down to univariate intersection numbers, and we know how to compute univariate intersection numbers. This is nothing but univariate intersection number between two-state forms is sum over the residue over this psi and phi r, which is the two rational function, where psi is the unique solution of this differential equation. And now the question is, what happens when you go for the multivariate case? Let's see the algorithm, what it happens, that now the integral is not a function of one variable, it's a function of more variables, and then we determine the number of masters, which I will come again. But then again, any integral can be written in terms of masters. This remains same. Only difference is that now earlier they were univariate function, now they are multivariate function. Once we choose basis, then one can define the metric matrix, and the master decomposition formula remains same. The difference is here that this is again identified as C, the undetermined coefficient, which we are after. And here all these entries are now multivariate intersection number. So now it boils down to how do we compute multivariate intersection numbers. And Sebastian put up the idea of computing this multivariate intersection number using recursive formula. That is, you you decompose the space into let's say two variables, and then you go in one space and then write the full intersection as a recursive formula of those variable. I will come to it slowly again. But first let me comment it out again on the number of masters part. As we have seen already, that the number of master is the dimension of the cohomology group, and the dimension of cohomology group is related to Euler characteristic by this formula. And thanks to Aomoto's vanishing theorem, that all the cohomologies vanish apart from k is equal to n, which is the middle dimension, and then the number of master is related to the Euler characteristic directly. And there are a lot of ways, as Sebastian also pointed out in his talk, also Pier Paolo, that there are many ways to compute these Euler characteristics. However, we will be, and also it can be shown that it can be written as number of solutions of omega equal to 0. But in the multivariate case, like omega will be a function of two variables, like omega, let's say think of two variables, so omega 1 dz1 plus omega 2 dz2. So in a sense we get the number of master by putting omega 1 equal to 0, omega 2 equal to 0, solving these equations. But for more, probably we will hear from talk by ALUFFI later in this case. So once we know the number of masters in the in any space, so how do we write the multivariate intersection number? So then I give you an explicit example. So let's say that we start from a integral like having a phi u. Okay, so this is the two-dimensional space, the full space X, which having z1 and z2 variable, and I'm looking the integral is, let's say, phi L and u, and I assume that in this space u has already regulated everything. So that means that u on the boundary is 0. So I remove all the divisors in this, and what we are looking for, the intersection number between phi L and the dual of it phi R in this space z1 z2 space. So as I said that the goal is, so basically the goal is to compute phi L phi R omega. And the goal is to somehow express it in a recursive way. So first, in a sense, like X can be decomposed in a sense what you call inner space or outer space. So first we go to the Z2 space, and then we do the one can use the decomposition of the phi L in Z2 space. So basically in Z2 space I also know the master integrals I can determine, like omega 2 equal to 0 gives me the number of masters in that space. And then I can decompose these two form into one form, wedge one form, where these are the masters in the Z2 space. Similarly for the dual 2 form also can be decomposed in this way, where these coefficients can be obtained by simple projections, and here you can see that these are intersection numbers in the Z2 space which are univariate, and C2 can be seen as this metric matrix in this space in the Z2 variable. And I remind you again that the intersection number in the Z2 space, which is with respect to the omega 2, is nothing but that the iota operator of EI wedge Hj. So the iota operator is basically maps EI to that with EI with a compact support in this space, and which ultimately boils down, which we have seen yesterday also, that is nothing but the sum of our residues psi I and Hj, where psi I is the solution of this differential equation. But now from here I can write psi as delta omega 2 inverse, and I put it here. I will say that why I am saying this. And so in the same way here I can write this 2 variable intersection number as iota of phi L wedge phi R, where these are two forms. And then if I use the decomposition of this here and here, then I see that basically it is decomposed in 2 space, one is in x1 and x2, and this we can quickly identify nothing but the C matrix, right? Because this was the EI2 Hj2 on this space, and this is C2, so I can write it as C2. And now what it boils down, that it is iota operator of phi L wedge phi R C2. So we can attempt to write it also will be the same thing, sum over of residue on the variable of which are the poles from coming from Z1 in that space. One can write it in this form, which is nothing but I have a new connection. I have so earlier the connection was like omega 2, and here I have to determine this new connection, and if I operate it on phi L inverse, then I get this formula. So I know how to compute. So the now the goal is how to get this, how to define this new connection, and as well as how to get this omega 1 that I show you in a moment. So let's consider, as I was saying, that we are looking for this integral which is phi L u. So earlier, okay, let me emphasize, when we determine this came from the equivalence. So we started with the u phi integral, and we tried to determine the equivalence class of phi, and there we found out that delta omega 2 xi, which is kind of IBP identities, gives rise to, they define the equivalence class of the phi, and from there we got the connection. So the goal is that in this case also to mimic that situation. So as I say, we start with the integral, and we use the decomposition of phi L, then we can write EI as the masters in the Z2 space, and I can write this integral where I dub this as UI. And then so look for this integral, which is integral phi L UI. Let's consider it. So I can try to define the equivalent, determine the equivalence class of this phi L. From there I want to determine the connection. So we start with a 0 form. So this is one form. So here we start with a 0 form here and try to mimic this. We have already seen probably yesterday from Yalte's one also, that this is 0. So then if I operate the d here, so I get d xi and ey plus xi I and dui. And dui, so basically I can write a differential equation for like ui here with this, with omega 1. And if I plug dui here, and if I plug delta ij here, then this becomes uj, and I can take out uj. So then you can see that I can determine an operator here, delta omega 1, which is the new connection here, which gives rise to 0. And the operator is now d delta ij plus omega 1 ij. In the case of univariate, it was d plus simple omega 1, and now it becomes a matrix. And now the question is, once I have the connection, so the thing is that how to determine this omega 1. So what we do, so let's operate, so omega 1 can be obtained, as we know that it is a differential equation. In this space we can determine it by intersection. So I show it explicitly like dUi. I can take the ui explicitly and operate the d, but remember this d is with respect to the variable z1. And then I operate dei, and the u is here, and du, and I take the common u, so it becomes d log u wedge ei. And there you can identify this as the small omega 1, which is nothing but the dz1 of log u, means derivative of the log u with respect to the z1. Then I can see that it becomes d plus omega 1 wedge ei2 u. And now I can consider it as this is u and this is phi, so I can try to determine how it will look in the z2 space where the masters are this. And then quickly you understand this is the master decomposition formula of this form d plus omega 1 ei, hj and c2 inverse, which can be identified as omega. So now we know what is the omega, we can plug it here, and then we know the connection, and then we can write what is the two variable intersection number. I show you in this slide again that the two variable intersection number then can be defined as the residue of the z1, and this p are the poles of this capital omega 1, and then I can write it as operator nabla omega 1 inverse phi li, which was the coefficient after the projection, phi rj c2ij. And now if you closely look, I can plug in the decomposition of phi r. Phi r decomposition has a c2 inverse, and then you can see the c2 inverse and c2 will cancel, so only this part, just to emphasize, this part ei2 phi r only remains. So the formula becomes formula takes a look like this: residue of z1 is nabla omega 1 inverse phi li1 and a intersection number, where it can be also written as in terms of psi, as we have seen also in univariate case like this, where psi solves this differential equation explicitly. So now we know that how a two variable intersection number looks like. In the similar way, one can write the n variable intersection just by employing this, like recursively decomposing the space in n minus 1 into 1 like this. So I quickly go through now the n minus 1 case, n form case intersection number. So here I assume that the n form can be decomposed into n minus 1 form, wedge 1 form, and I assume that this n minus 1 form is completely known to me. So so this again the phi ln like earlier, and when I say that I know the n minus 1, what we know exactly? I know the number of masters, the dimension of the cohomology group in that space, and I also know the master basis in that space, and then I can determine also the metric matrix between them. That is, I am able to evaluate n minus 1 form intersection number there. So once these are known, so then phi, so I can determine these coefficients by just simple projections, and you see that all of them are n minus 1 form intersections. So I can determine this. And as now here is a change from the earlier formula. So now you can say that why we did that. So earlier when I showed you this formula, that this was the differential equation, right? And what we were trying to decompose was u phi l, and let's say that I have a family of integrals. When I want to decompose them, so every time this phi l will change, so every time I have to plug in a power series solution of psi I and solve this. However, the phi r on the other hand was arbitrary, the dual space. So I can change, so I know that intersection number is invariant. So from phi l phi r I can also there is a relation with phi r phi l to phi l phi r with minus omega. The omega is just change the sign. So I can use phi r here, and I keep phi r as the same for all of the integrals, where just this differential equation, when I get the solution of psi I, this remains same. So for all the integrals I can use the same power series solution here, so which helps in the computation in the forward. But in this case for one integral you have to do it, but if I want to do two integral reduction, then if I write it in terms of phi r, then I don't have to solve the power series again here. So that's why we change the formula in a sense on the phi right, the dual form. And so you can see that so the psi actually comes from the differential equation of the phi r, and you see with a minus, because I said that they are related with a minus sign. And also we have to take care of the minus again here, but you see that earlier it was del z n plus omega n acting on this one, but now they have changed the position in this case. And this is the formula with which you can compute the n form, because then you can do a recursive, like you take the n minus 1 form and you assume that it can be decomposed into n minus 2 and 1, n minus 3 and 1 again. So this way until you reach the 0 form, just the plain functions, and then you can get down, then you can again get back to your n form intersection numbers. So these are the main formulas to show that how one can compute the n form intersection number. But in our, it can be also written in many ways, like we saw that basically it can also look like this, where using the properties of linearity of residues it can be shown that it looks like this. But okay, I'm not going into the detail of this. Let's see some examples now. So let's see that we know that how to compute the multivariate intersection numbers, then how, when we apply from a Feynman integral, how it goes. So I will show you an example. Let's say for example the one loop massless box. So we use, as I said, the bicurve representation of the Feynman integral. So we take the this is a massless box with the propagators z1, z2, z3, z4. Okay, these are usual k plus p1, k plus p1 plus p2, k plus p1 plus p2 plus p3. Then you can obtain the bicurve polynomial of this, as Hjalte has already showed the formulas. I am not going to, so I will just say that this is the uz. Now you can see this is a function of z1, z2, z3 and z4. So it's a 4 variable is there. And now we can determine, as I said, the number of masters. So we go to each sector, like when I say sector means you can put cart, and then you can determine the numbers of master integral in that sector only. And then you see that there are basically 3 masters which you can choose as the box, and these 2 bubble S and S channel and T channel bubble. So your integral decomposition says that any integral can be any integral like this box with different powers of propagators can be written in terms of box and these 2 bubbles with these undetermined coefficients. And now we have to determine this C1, C2, C3. As I said that as we already know that this comes from the master decomposition formula as we have seen earlier. However, the only difference is that we compute multivariate intersection number. And one thing to point it out, like I can use the cart 1, 2, 3, 4, so that only this remains, and then I determine C1, and similarly for 1, 3, 2, 3. But however, we see that if we determine only 1, 3 and 2, 3 cart, then C1 is already determined from both of them. So in a sense, like which is called the spanning set of cart, or like this, that you determine the minimal number of carts which I have to operate on this equation to get all the coefficients. So in a sense here we see that there are basically 2 carts are needed to compute all these undetermined coefficients. So let's check. So our goal is, let's say, that to reduce this integral, which having 2 dots, 2 higher power of propagators here. So first we say, as I said, that we look what happens at the cart 1, 3 when I put z1 and z3 cart. So this integral on the cart can be written as u13 phi 13. Just the labeling is there. That means the cart has been applied. So what does it mean in the cart? You see that the bicurve polynomial, which was the full bicurve u, and I put z1 and z3 0. However, in this case, if you put it and the integral, there is still the denominator z2 and z4, and then we have to regularize the u, because the phi actually contains this 1 by z2 and z4. So that's why we regularize with some generic index, as Sebastian also pointed out this in his talk. And we define u13 as this and phi 13 as this. So then basically u13 regulates all the poles of phi 13 in a sense. And at the very end of the computations, we put these regulators to 0. So it goes like this. So the first thing is that you have to determine the number of masters. So in this case, as we can either first do the intersection in Z2 space and then Z4 space, or we can do otherwise also. In this case, we determine that, let's say, first you do in Z4, that is when you have, these are variable of Z2 and Z4. So your omega, when you determine, it's omega 2 and omega 4. So omega 4 equal to 0 gives me 2 solutions, which boils down to 2 masters in this space. And then also we can see omega 2 and omega 4 both equal to 0 gives me 2 master integrals, which goes with our observation. And then in this space, in the Z4 space, we can choose these bases, and in these examples we always choose the form and the dual form as same. So there is no H, all E and H are all same. and we choose basis here like this, and here these masters are connected to this. 1 by Z to Z4 connects to the box, and 1 connects to the bubble. So, and then C1 and C2 from the master decomposition looks like the combination of these two intersection, one intersection matrix and both intersection matrix, and these are two form intersections, and they can be done using those formulas, and once you plug in all the intersection numbers, then you get this coefficient, and one can check with many publicly available codes, IVP codes, that they agrees. Similarly, there is we can go for the CART-24, and in this case also we go like same, so that we define the integral u to u and phi, and then again we regularize u by putting, because then here z1 and z3 remains as denominator, so we put regulators on z1 and z3, and we determine for this integral what is my phi. So then the integral becomes u phi, and this is a two form intersection. We again go like this. So we first do the integration in z3 space and then the z1 space, and we choose this as base forms in the z3 space, and then these forms corresponds to the master integrals in this space. And then again these coefficients can be determined by this combination of this intersection matrix. Here one thing, it also solves a purpose that it can be checked that you get C1 from the CART-24, and also you get C1 from here. They both should remain same, kind of like cross check of what you are doing makes sense or not. So that means that any integral, like one loop integral, so you give me any power, it can be completely decomposed. I can determine all these coefficients by multivariate intersection numbers. But so not only that, we can also determine the differential equation of the massless box also. So the differential equation looks like the differential of this box can be written as again the sum of these master integrals, where this box is the bicurve with a prefactor, but now as we are taking derivative with respect to s, so we have to be careful with the prefactor, where k is just a prefactor of s and t. And similarly, as I have already explained, that there are two cards which is able to determine all these coefficients a1, a2 and a3. So we do the same exercise here with at first CART-13. So then delta s of the box on the CART-13 is nothing but like this. Only change will be u13 will be same. Only thing is that pi will change this time. As you can see, pi 13 is now f by z to z4, where f can be identified as this. Earlier only phi was omega 1 by z2 square. And then you go exactly the same procedure. You go in the z4 space and you find it out the number of masters. You find it out the base forms there. Then you compute all the necessary intersection numbers, C1 and the projections and these. And then you come to the z2 space and complete all the intersection numbers. As I said that, I mean, these can be written as recursively intersection numbers in this Z4 space. And then A1 and A2 can be identified as the combination of these two intersection matrix, and then we can, after putting, I must mention that after putting the row 2 and row 4 to 0, we obtain these numbers here, and they can be also easily verified. Similarly for CART-24, I will show it again, but the procedure is same, that we determine the on the CART-24 these coefficients A1 and A3, which A3 was undetermined and A1 can be compared with the other 1, 3, and we see that it is same. So now we obtain the one loop, at least one example we see at one loop, that when we obtain the full decomposition of any integral as well as the differential equation. Now let's see what happens at two loop cases. So recently we managed to obtain this the reductions for, let's say, two loop non-planar massless triangle. Everything is massless here. So P1 square and P2 square is 0, P1 P2 is by 2, and these are the denominators, and here there is only one ISP which we take as K2 plus P1 square. And here you can see there are 5 master integrals. One can determine them sector by sector there, and we choose the masters as these 5 integrals. So now one can say like any integral can be written as the linear combination of these master integrals. So our goal is to determine now this C1, C2, C3, C4 and C5. And again here we can see quickly that basically I need 4 spanning set of cards to determine all these coefficients. This one is not needed because any of them this will survive, and I can always get C1 for all of these, at least for these 4 cards. So I go one by one again. So first I do the card 1, 3, 4, 6. So now you can see like this is the integral which you want to reduce, like with Z7 here in the numerator, and then this integral on this card can be defined as U1346 51346, where U1346 and there 1346 in a sense when you cut it in the Bicorp representation, in a sense they put to 0, so the only remaining is Z2 and Z5. So you regulate those things from phi, and you regulate the U in this sense, putting the regulators here, and then we determine what is your phi for this equation, which is easy, Z7 by Z2 Z5, we can very easily quickly see. So then this is a 3-form intersection. You can see that there are 3 variables, and then we do it first Z2, and then I mean in a sense like that space is decomposed in a sense, first Z2, then Z5 and Z7, and we choose the basis. So in the internally, like as the say that the form and dual forms at the moment we keep same, so there we do not choose dual form separately, we keep E1 and H1, E and H both same, and this can be identified as this integral, and this basis can be identified as this integral, and then C1 and C2 is from the master decomposition is like can be expressed as the combination of these 2 intersection matrix, and these are 3-form intersection numbers. We determine them using the formula as I described, and then one obtain this number after putting row 2 and row 5 to 0, and then we can determine C1, C2. Similarly for 2, 3, 4, 5 cut also, only the change is the integral, because one has to every time change the regulator, properly regulated, and the phi. This is also 3-form intersection, and you see the number of masters is 2, 2, 2 in every label, and we choose the basis like this, and then we can determine also C1 and C3 using the 3-form intersection. And going back to coming down to 1, 3, 5 cut, now it becomes a bit more, it's 4 variable intersection now, and it goes in the same way. We choose forms and every label, we choose the basis form in every label, we determine the number of masters, and the number of masters in this case is like first is 2, then 3, and then ultimately boiling down 2. So this agrees with this observation. Similarly for cut 2, 4, 6, this is also 4-form intersection. We show it here, and we obtain the C1 and C5 correctly, which can be related to I mean which can be checked with any public codes. So in a sense, so with these 2 examples I show you like at least 1 loop example and a 2 loop example how one can get the full decomposition, and also I show you that even till 4 variable intersection numbers one can compute, and they can be used to determine these coefficients. And not only this, we have already also computed this, and also like I want to mention the even massive box, 1 loop massive box till the full decomposition till tadpole we have managed to do it, and also there are more work in progress we are trying. And then it comes to the summary and conclusion, let's say. So we see that the algebra of Feynman integrals, we can say now this controlled by intersection numbers, and intersection number is like kind of scalar product between Feynman integrals, and we are exploiting the geometric properties like Bicorp polynomial, and it can be extended to other representation, and this is useful for both physics, mathematics. And we saw for the first time that a direct decomposition of Feynman integral in integral basis. Also we construct system of differential equation for this integral basis. We do not need any intermediate relations like the IVP relations. And for further outlook, I will say like obviously there are many works to do. One is that one can check that whether the Bicorp representation what we are using is the optimal one, or there are other integral representations like Feynman Swinger parameter, and in those cases what happens, how this thing goes on. Also there are some new thing like quadratic relations, as Pier Paolo mentioned in the first talk, using this twisted Riemann period relation. Also Stefano will touch upon this quadratic relations, how it can be obtained or how new things can be seen there. And I conclude with this slide, which was also goes like what Professor Yoshida was mentioning. Pier Paolo showed me actually one day that, look, this is comes from a paper like what Wigner was referring to, the mysterious phenomena in which areas of pure mathematics, which was constructed without any regard to application, suddenly discovered to be exactly what is required to describe the structure of the physical world, which we see that intersection numbers can be related to these coefficients which we are looking for in the linear relation of Feynman integrals or even in differential equation, and maybe furthermore we see something more. Thank you.
Hello. Yes. Okay. Could you please a bit more, I don't know if you have time or if it is possible, what exactly this regularization, how exactly is used? I mean, because you didn't show anything special, so which of course is related to how you define your integrals or maybe your forms.
So the thing is that the integral is u and phi, okay? So when we look for this, we have to remember that there are some assumptions in these definitions that the poles of phi is in a sense already contained in the poles of omega, which comes from the d log u. So in this case, let's say if you don't put the regulators, that phi has a 1 by z2, z4. So the z2 and z4 has poles 0 and infinity. So one has to take care of those poles, regularize in terms of the integrand, because all the information comes from the integrand and the twist. So that's why we have to put a generic regularization here just to take care of the poles, so that this integral, then we can use the intersection theory on this definition of the integral. That's the reason that why we put the regulators here.
Where exactly it influences your calculation?
Where?
Where exactly influence your calculation?
Because we defined as u is there, then the omega has the rho and rho 2, rho 4, rho 5, the omegas, which the small omegas, as I said, they have these numbers there. And these omegas goes into the intersection, right? When I compute the intersection, there are omegas.
If you put 0, what was the difference?
Wait. Oh, sorry, not this way.
You have at some point to sum over the poles of omega. Sorry, I'm breaking in.
Yes.
And if you don't put those regulators, those poles of omega are just not all there, so you miss some contribution.
In a sense, like from here.
Yeah.
Every level, I mean, as I said that even univariate, it was like, okay, I can go ahead a bit more. Oh, sorry, no.
Okay, it's a bit confusing. Maybe we can discuss.
So like here you see that we integrate over the poles, and these poles comes from the omegas, right? So if they don't have the correct all the poles there, then we'll miss some contribution, as Yalte is saying also. Okay.
Thanks. I got a comment and a question. So the comment is regarding these extra regulators. So I was thinking if you introduce these regulators anyway to do the computation in these cases, then instead of throwing them away, you could just keep them, and then you have a symbolic reduction for arbitrary powers in one step, right? You don't have to do any pre-calculation. That was just the comment. The question was, the key step here is exactly on the upper left corner on this board, right? When you decompose your integrands into forms in the fiber and on the base.
Yes.
So I would assume, so I know what happens in a case that's called linearly reducible, right? And then you know you can find a D-log basis in each fiber. So are you using such a kind of decomposition, or how do you choose this step?
So, I mean, mathematically, I think Sebastian tell more like how when this decomposition can happen or not. But at the moment, I will say like we do by experiment. I mean, we choose like at the moment. Okay, is your question that how we determine this? This decomposition of the space, that which space I choose here first and this thing. Okay, this we determine at the moment, like if I go here, let's say for example, okay, this example is like we determine, so let's say first we assume that Z4 is the fiber, and then we determine the number of masters there, and we determine the masters here. And also I can do the first the Z2 space and the other space, and we check that if the number of masters, which gives me lower in a sense, so that I have to compute lesser number of intersection numbers. But mathematically, probably Sebastian can comment more that how it can be decomposed in which fibers.
Yes, so the question relates to this step. So when you want to, for example, do a partial fraction decomposition in this Z4 on the first variable, then you will introduce the discriminant, like the new denominators in the other variable, right? So my assumption would be that if you do this fibration, at each step you're working on a space where you have cut out a ton of extra hypersurfaces coming from singularities that you see. So my question is just, well, maybe we can discuss this later, but yeah.
I think you can always choose a polynomial basis.
Yes.
Okay, are there any more questions? Okay, if not, let's thank Next talk is by Simon Caron-HUOT on the Poincare dual of Feynman integrals.
Yes. Yeah. No.
Switch it off.
Can you hear me? It's on. Yes. So, well, I'd like to thank the organizer for putting up this great workshop. I'm going to be talking about work in progress with student Andrew Pokraka. I presented a poster on this last summer at Amplitudes. This talk would be much easier to give if the paper was out. What happened is that every time we kind of get together to write that paper, we realize that there's a lot of important and basic things that we don't understand correctly, and then we try to understand them. Now, hopefully, we have a coherent story that I'm going to tell you. Yeah, so I'm going to start by writing down the messiest equation in this talk, which is somehow our general goal. So what we're trying to do is to start with an amplitude, which is a function of external momenta and the dimensional regularization parameter. And okay, it starts life as some integral over d-dimensional loop momenta to L of some integron, which is a function of external momenta, the internal one, and maybe epsilon. And our goal is to rewrite this integron in terms of a sum over coefficients that are function of the external momenta and epsilon. So these are p and epsilon times some basis integral fi that basis integron that depends on these things. Okay, so that's the general goal of what we're trying to do. The important thing to note is that this integron here is always a rational function. These coefficients we're trying to extract are algebraic. The algebraic function of p, they're rational in epsilon, and the general idea of this workshop is that, well, our shared goal is to try to compute these coefficients algebraically. This integral ultimately are supposed to be integrated over a physical contour, but these coefficients have nothing to do with the contour. They're just statements about the integrand. And the idea is that we can extract these by computing intersection between some dual of the Feynman integral f with the integrand. Okay? And the basic question that I'm after is, what is the space that this dual forms live? What's the coefficient? Basically, these f are like the coefficients. What space do they live in? What's the proper space? In this talk, I'm going to keep epsilon not equal to 0, so I have dimensional regularization turned on. However, the difference compared to the previous talk is that I'm not going to have these deformation parameters. I'm going to work as much as possible directly with the problem as set up by Etoffe and Veltman. I would like, people who know me know I hate the reg viscerally. I would like to be able to not do that. I will talk at the end, I will say a few words about the epsilon to 0 limit at the end, but for this talk I will work with epsilon. Okay, so that's the setup. And the short answer to some of the brief summary of the talk is that these forms here are going to live in some de Rham cohomology that is with compact support of the complexified loop momenta, some dimension, minus some subspace that I'm going to tell you shortly. They live in that space. Now, nobody likes de Rham because, our goal is to do algebraic things. De Rham is not algebraic. Okay? The claim is that all the representatives we're going to need are these nice distributions times algebraic things. So for all so we're going to be able to span the basis of this de Rham cohomology in terms of things that are completely algebraic times these distributions. So let me introduce you friends. Okay, let me say a few things. Okay, so in the spirit of this workshop, I'm going to try to share what I know about these things, what we understand finally. I'm going to be saying, so basically with hindsight, I think everything that I would say would be completely trivial and obvious. So I'm about to say some things, and to some of you, they will indeed feel obvious. So if I succeed this talk, you will leave and you will think, I knew this, I always knew this, it's obvious, it's evident. Okay? But if I say some things that look weird to you, just say that nonsense, don't stop listening to the talk because I'm saying nonsense, just stop me. Okay? It's supposed to be, I'm going to be saying very simple things. Okay? So these distributions, what are they? So the first one is a step function that is, so we're going to have singularities, and we're going to need to put 0 on the singularity, and this step function is 1 outside the small disk. Okay? Fair enough. That's like a regulating thing. Then we can take the derivative of the step function, and that's like a delta function that lives in a circle. Fair enough. And the third guy is a delta function that lives on a point. That's a two-dimensional delta function. That's a two-formed. Okay. So let me explain the last guy a little bit more. I'm going to play an important role later. Okay. So the last guy technically is, it is minus pi times delta function of the real part of z, delta function of the real part, imaginary part of z, times dz wedge dz bar. It's easy to see it's closed because it depends on two variables and you have two dz stuff. The normalization is such that 1 over 2 pi I times the integral is 1. That's what you want. Okay. If you don't like delta function, think about if you prefer your de Rham cohomology to be smooth function, think about a bump. It doesn't matter, I prefer delta function. So, as an illustration of what you can do with that, one obvious thing. So, for example, if you take the simplest cohomology, H2 de Rham compact of CP1, well, this has one generator, as everybody knows, and that generator I can take to be that form at some, I pick any point I want, the delta function is equal A, that's that form. If you're taking real cohomology, that's an obvious statement. So basically, you start from a sphere. To form on a sphere is like a density of something. So you have some density of stuff on a sphere. And then it's obvious you can deform your sphere to push all your density and concentrate it into a point. Right? So it's obvious that any two form on a sphere is cohomologous to a delta function. You just shrink the whole density to a point. It's also obvious that you can take density at a point and move it around. So this cohomology class does not depend on the point A. I want to say more. What I want to say is that all the operations we'll ever need to do with these things are algebraic. For example, to see that this class does not depend on the base point, we just need to find an algebraic form whose derivative is that. That algebraic form is simply d of, if I take dz over z minus a minus dz of z minus b, by the very famous holomorphic anomaly, this is delta 2 of z minus a minus delta 2 of z minus b. So it's obvious that this form does not depend on the base point, and you can prove that algebraically. So this is a form that you can manipulate using only algebraic operations. And that's what we'll use. So until we're talking the RAM, operationally everything we do is algebraic. Okay. Questions? Okay. Yeah. So I'm going to be telling you about how to apply this for Feynman integrals. So I'm going to tell you what we mean by Feynman integrals. I'm going to introduce two basic maps, like this regularization, but slightly generalized. I'm going to be talking about, then because it's a Blackboard talk, I'll be talking about one loop generalized unitarity and some applications. So in particular, when you have this singular fibration that were mentioned in the previous talk, you can actually, when you can linearize the Bikov polynomial in some variable, you can use this to your benefit. Yeah. Yeah, because there's a z-bar dependence secretly in that. And a good way of seeing, there's various ways of seeing this. Basically, this equation is due to Poisson. So if you take the Laplace equation in 2 dimensions, you have something like grad square of log of, so the value of x square is equal to 4 pi a delta function at the origin. There's then log of the 1/r potential in 3D. So you know, Poisson and Newton knew that basically. Okay, so if you're not familiar with it, think about it. It should be, it's a simple equation. This thing is 4 del bar d. So this is telling you that basically del bar of d of that is 1 over z. So basically, yeah, so d over d z bar of 1 over z is pi times the delta function. So that's that equation. Okay, it's a very important equation. It's basically Gauss's law for electrostatics in 2 dimensions. Yeah.
In mathematics, D.
Yes.
You have a holomorphic one and anti-holomorphic one.
Yeah.
So you have a summation. Total points.
Yeah. So D here is del plus del bar.
Oh.
It's the full D. Thank you. Yes. But here I took only the dz part. If I add the dz bar part, they will cancel out. but the point is that I'm only ever going to write algebraic forms. So I'm never going to write the dz bar explicitly. All the dz bars are hidden here and here. I will never write a dz bar. Only d thetas and delta. Yeah, that's the point. This is not holomorphic. This is not a closed form. That's how you can use it to change H2. It's very important. Normally you don't allow one form. If you're computing H1, you're not allowing one forms with single poles, with residues, because they are not closed, which is exactly what we're using here. Good. Okay. So that example was important. Now let me explain Feynman integrals. Well, what I'm going to mean by it today. Okay. So we write this measure all the time, d minus d of 4 minus 2 epsilon L. What this means for us is So there's 4 components, a DL1, wedge DL2, wedge DL3, wedge DL4, and then there's some extra dimensional component, minus 2 epsilon of them. The important thing is that the physics only depends on the radius of the external dimension. So we have d of L perp square. That's the radius of the external dimensions. But then there's supposed to be minus 2 epsilon of them. So just to get the correct scaling, the radial direction needs to come with this power. This is what we mean, and also we usually normalize by including the volume of a sphere in minus 2 epsilon dimension. All of these are defined for continuous epsilon, and this is what we mean by one loop integral in general dimensions. Notice that it's a 5 form. Okay, it doesn't matter what epsilon is, this is always a 5 form. Okay, you have u usual 4 plus L perp square. That's what we need. At 2 loops, you can generalize this. If you have this, then of course you get the same dl1 up to dl1 perp square over this thing, and then you get dl2 1 with the dot dl2 perp square. However, yes.
Excuse me, you've made an arbitrary choice of your loop momentum at 2 loops. I mean, you have to choose how to route your loop momentum.
No, because that's the next thing. There's a third thing that you have to put is the angle between them.
Good.
So there's an angle that I have to put there. That's L1 perp dot L2 perp. So I'm going to parameterize the angle as the cost of the thing because that's the only thing I care. And then there's an analog of this measure factor, which is just the ground determinant. Good. So we get something like L1 perp square, L2 perp square, minus L1 perp dot L2 perp square to the minus epsilon again. Actually, there's some integer shift, so yeah, some number minus epsilon. So that's a 2 loop integral. Notice it's an 11 form. It's not 10 because we have this extra angle to integrate over. Okay? The pattern should be obvious. And you can find it, so for example, the derivation of the Bicroft representation in a nice short paper by Pierpaolo and Sebastian. You can read if you want to see it explicitly. But yeah, you can keep going. So that's a short answer. So when mathematicians ask sometimes mathematicians ask what is a d-dimensional integral, that's what we mean. So, and from that, you can derive all of these parametric representation, Bicroft, and so on. All of these other representations that will appear in the lectures, they can all be derived from this derivation, from this definition. Okay, but for this talk, this definition is going to be advantageous because remember, our goal is to calculate coefficient by integrating this dual form against the total the sum of all Feynman diagrams. And all of these representations, they're tied to a specific individual integral. I need something that I can evaluate for all integrals together. So to evaluate some, yeah. So I need to use this in this talk. Okay. Great.
But you're saying that's like completely routing independent.
It's completely routing independent because this, for example, this ground determinant is invariant if you take L perp 1 and shift it by L2. Yeah, this ground determinant is routing invariant. It's a property of that factor. Yeah, exactly. So I'm assuming that the external have p perp equals 0. So all the external are inside 4 dimension. If you want to generalize this, then you will have to you need more DL stuff explicitly, and you have higher form. Thank you. But in physics, whenever these momenta represent those of resolved particles, which is all you need to calculate the renormalized.
So just from my curiosity, when you have external momenta in perp, let's say, how
Depends how many perp you have, independent perp you have. They have to be, you need to...
choose a frame where you can, let's say, have you done this exercise? How much is the form?
Well, it's whatever you need for the bicurve representation. You know it. But the point is that for physics, you don't need it. You observe particles are in 4 dimensions.
Academical, let's say, what is it?
Yeah, well, you can read the paper by Bykov. I don't remember. Someone can tell you the number. It's just a combinatoric thing. It's going to go like L plus internal plus external times internal plus external plus 1 or something. I forgot the formula. We can talk later.
Yeah.
Okay. But yeah, I'm going to be sticking to the setup. Okay. So let me explain the tools. How these forms are going to appear. So first, let me define. So I've defined integrals precisely, and as you see, for general epsilon, you have a twist. This is what I call the twist function u, and a 2 loop is this Bicurve. Is this gram determinant, the epsilon. This is the u, and everything else is single valued. So all the multivaluedness is in that factor. Okay. So usually we define a connection that's d log of u, and the Feynman integrals live in the cohomology of n, where this n is this number 5, 11, and so on, of complex phi loop momenta, that is Cn, minus, we have to remove the place where L perp is equal to 0, or in general u equals 0, and we have to remove the place where propagators blew up. So our Feynman integrals have denominators which are always of the form, just to say it once, they're always of the form 1 over b, which is something like 1 over some L minus p square, maybe with a mass. And this thing here is always going to be of the form L perp square plus sum from 1 to 4 of L1, Li minus pi square. So it's quadratic in the Li's, linear in L perp square, plus the mass. Yeah. You may notice that this is linear in L square and Li. And this is the starting point of the bicurve representation. Using it as linear, you can find the linear rotation, which trivializes all denominators. But then you're pushing out the information into that twist, which gives these awful polynomials that were mentioned. But yeah, today we're just going to work directly in this form. So the Feynman integrals live in that cohomology. And as has been explained by Theof and Veldman and reviewed, there's never any boundary surface terms in integration by parts. And yeah, it's twisted by this omega. So we really could just care about the cohomology class. So yeah, integral of u times grad of some form is equal to 0 by integration by part identities. Now, where do the dual forms live? The claim, the idea, is that the dual forms have to be something we can integrate against this. And the space, so this is, you could think of as Hn the RAM here. And here it's again Hn the RAM, but now compact support of exactly the same space. Okay. One comment is important. So notice that because I work with rho not equal to 0, so there was a statement in the first lecture that these spaces were basically the same up to reflecting omega. So you have to reflect omega so that you can multiply these things and get something single valued. But these spaces are not identical. In the case where you have this general twist, you're like in a generic situation, and then they are identical. But for the problem I'm going to study here with no deformation, they're not the same. And one of the points is that this dual space is actually much simpler. In particular, all of these dual forms are going to live on cuts. as we. That's what I want to explain. Okay. Yeah. Questions? So that's the space we're trying to define. I'm going to need to introduce two tools which make use of these, our friends, these distributions. Yeah. So our first tool is this compact support map, which is the map that Matsumoto and Cho define reg. I'm not going to call it reg because in physics it always means something else. So it's a compact support map. Its point is it takes a representative phi of Hn of some space minus some stuff, and maps it to the compact support version of the same space. For the generic twist case, this map is an isomorphism. That is known fact. Here it is not. So I want to explain a bit this map so we can see that it's not. Okay. So the way we can compute this map in practice, so let me give an explicit example. So if you're talking about H1, we're going to be talking about H1 of, say, CP1 minus 4 points, 0, 1, x inverse, infinity, so the hypergeometric sort of stuff, where now the form is not going to twist x inverse. Okay? So the form is going to be, say, alpha dx over x plus beta dx over 1 minus x, but x minus 1, and sorry, dz over z, z is my variable, z over z minus 1, but there's no dz over z minus x inverse. Okay? So there's no twist, there's a point that's not twisted, so that's a special case of the hypergeometric where it degenerates and you get like log in the series expansion at round 1. In this case, suppose you have a form that's element of that. You regulate it, then I use this notation, put subscript C. You simply take the form phi and you slap a bunch of step function to fix it up. Okay? And I need to remove a little hole around each of the triangle points. So theta of z, theta of z minus 1, theta of z x minus 1, and theta of 1 over z to fix the 4 singular points. Okay, I'm just re-explaining the Matsumoto-Cho procedure. Nothing new here, but it's going to be important. There's going to be a subtlety. Okay? So that's basically what you want to write, but this is not closed, so you need some patch-up. And the way to calculate this patch-up is you calculate grad of this thing, and you find that, so grad phi is 0, but then you get phi times grad theta, and so with a minus sign because of sign. And grad theta, so it's just d theta. Theta, theta, theta. So you see our friend. Sure. So you get a little problem around the points we excluded. But now it's obvious how to fix that. So this catch-up is going to be plus a d theta times some primitive psi. And if you collect the d theta on grad, then you find that problem is fixed if grad of phi is equal to our original phi. And this coordinate will be a good form. So psi is 1 over grad times phi, it's the inverse. And its point in life is that because of the d theta, you calculate this, so psi I, you calculate as a Lorentz series around near zi. Okay? This is something, these are the 4 singular points to do this series. And how many terms you need in the series is going to depend on like how many powers of propagators you have in your order form. But in principle, you can do it to our orders.
Sorry.
Yeah.
So for this kind of Lorentz expression, I have up to power get some kind of generic formula.
Yeah, so you compute whatever order you're going to need.
That's an arbitrary symbolic problem.
No, you cannot do it symbolically. So yeah, if you want to reduce finite integral with some cubic propagator, you need to work some order, and then if you have a quartic propagator, you need to work order. It's always the same story. Yeah, this is you can only do that locally. Okay, but you can. But yeah, for any given problem, you can always do it. And so that's this reg map. But now what you see is that if you have if you're close to the yeah, we're supposed to work in the dual space where I have no poles at 1 over x. But yeah, assume there's. I'm looking at the dual space where anyway. So yeah. So our map is really from h1 of CP1 minus 0, 1, infinity to h1 compact of CP1 minus the 4 points. So that's really what that map is. But now what we're going to find is that near x, near z equal x inverse, this grad is a 0 mode. So yeah, phi equal constant is there's a constant ambiguity. Constant 0 mode. Well, it's constant plus dot 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 0 mode. So there's a parameter. So what you do with that is that given a representative phi, there's a unique choice where you put this constant 0. So given phi or as a form, there's a unique phi c. Unique if the d theta of zx minus 1 multiplies zx minus 1 to the 1 plus dot dot dot. So we insist that the constant term is not there. And then it's unique. Okay? So given a form, it's unique. But given a cohomology class, it's not unique. Because if phi 1 minus phi 2 is grad of g, then the representative of phi 1 minus so the compact support of phi 1 minus the compact support of phi 2 is naively the difference also going to vanish at the step function. So the difference basically is grad g times the step function on the outside. So which plus dot 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 near the singularity, which is cohomologous to minus g d theta. Minus g evaluated at the singular point. So the change between those two things is a form that's localized at that singular point. Okay. Now let me tell you a basis about this. Let me give you a basis about this space. So this solidity is important because otherwise you can get very confused. But the rule is actually very simple. You just integrate by part and pick up the d theta, which are like boundary terms. So if you have like a boundary at x inverse and you do integration by part, you have to keep track of that surface term. It's not a map of cohomology. This is something I'm going to use to calculate given a representative. I'm going to get this is very important. So the map does not exist, which is why at the beginning of the talk I said that the thing I'm going to compute, the thing that exists is this compact support the RAM. This is what I want. Okay?
Can you explain why you're defining a map?
I'm defining this map as a way of generating particular representative of that cohomology, particular forms I can work with.
But in general, the map doesn't exist. There is no map from cohomology to cohomology to practical time.
This is a map to forms, from forms to cohomology. What's the name for forms? Cycles, B something? Okay? I'm using this map, I'm using the image of this map to span this cohomology.
You're trying to construct compact supported forms.
Yes. Okay. That's a way of constructing examples of some forms. And they claim that they will span everything.
Okay, that's not well defined. It doesn't give a maximum cohomology.
Yeah, it's not a maximum cohomology. Just a way of getting forms.
Okay, because you wrote cohomology.
It's just a way of explicitly writing forms. Thanks for that's very important. So, and this is why, so I started the talk saying that this thing is not isomorphic to the other one. There's no isomorphism. It's really, it's a dual space. They're Poincare dual. This space is Poincare dual to the other space we care about, but it's not isomorphic. Okay. Okay, so I try to move on. Okay, the other map I will need, that one is completely well defined and canonical. If you have a submanifold Y inside of X, and if you take the compact support cohomology of that submanifold minus some stuff, this is basically the Leray delta map that, so if it's a k-dimensional k-manifold, you get a form in Hn plus k of compact support of X minus same stuff. Whatever stuff you remove here, you also have to remove on some manifold, obviously. This map is always well defined because you basically take a tubular neighborhood of Y. So that would be the Y direction, that would be some perpendicular direction, and you just draw a little tube. And sorry, I should not touch, obviously. It's a small tubular neighborhood. And what you do is you just wedge, you just take a form and you wedge it with these d theta of the perpendicular direction up to k of them. Okay, wedge this form. And technically, this is the pullback. So if you have a tubular neighborhood, you have a projection into your base manifold. So this is phi of, I don't know, wrong, composed with this pullback phi, the pullback of phi, and there's also, you have to integrate the connection from your reference point. So there's some small details, but basically it's just wedge d thetas. That's a form which is supported on a small cylinder. Okay? The idea is that H compact the RAM is spanned by image of C and delta, these two maps. So if you give me an algebraic form on a submanifold, I can take its image under these things, and I'm going to get completely well-defined forms that are going to span this basis. Let's apply this to one-loop integrals. These two maps are quite important. So they're the machinery by which we do all our calculations. So, for example, the key lemma is that if you take, so for example, at one loop you need H5. H5 of the C5 minus the twist and no pole. If you only remove the twist and no propagators, that's empty. So this is saying that if you don't have any propagator, there's no integral. All the integrals you can do gives 0. That means that, well, all of the image are going to be, everything's going to be spanned by delta. So this delta map from a cut propagator. And something else which is useful is that you have C5 minus U equal to 0, and one massless propagator equals 0. That's also empty. So if you just have one massless propagator, there's nothing you can get. So if you have massless propagator, you need at least 2 cut propagators. So this explains immediately why is H5 of C5 minus, I can immediately compute this. So basically, it's gamma is d1 up to dn is spanned, well, at most, but it's going to be trivial to show that they are independent, spanned by basically delta, spanned by delta of k greater than 2 propagators. So basically they are cut propagators. Let me give you an example. So the simplest form is going to be the bubble of the dual of a bubble.
If everything massive.
If everything massive. If everything's massive, then you will start at 1. If you have a type 4. So the dual of a bubble is simply the image, this data map, of a volume form on the bubble cut. The bubble cut in 5 dimensions is just a tree sphere. So you have a volume form of a tree sphere, which explicitly, if you take coordinates that are perpendicular to your thing, to be dl2, wedge dl3, wedge dl4, over 1 minus L1 square, minus L2 square, minus L2 square, maybe not 1, maybe some radius square, and there's some power, which I'm going to take to be 2 plus minus epsilon. The epsilon is flipped, because that's the dual side. And I put a 2 here, because actually the nice dual of the bubble is the 2-dimensional bubble. You can play this, you can choose whatever form you want, and do dimension shift as you like, and this one is nicer. But yeah, this, so the bubble dual is this, which is basically d theta of one propagator, wedge d theta of a second propagator, wedge this 3, 4. So that's the dual of a bubble. And that's the thing which extracts a bubble coefficient. Now, if you think for a second about this space of cohomology with a sphere, you realize quickly that it's one-dimensional. So we immediately have a basis for all the, we immediately have this basis here, which is basically the sum over all the bubble dual, triangle dual, box dual, and we're looking for a 5 form, so we're going to stop at pentagon dual. Right? And that's it. We stop there. There's something else which is obvious, but okay, I will take a second. Is that it's rather immediate to show that the coefficient, I'm going to show it in a second, but basically the coefficient of this pentagon dual is proportional to epsilon as epsilon goes to 0, so you don't need it in 4D. So this is really epsilon, so this basic integral is basically epsilon times a 6D pentagon, which is just 0. So you can, but yeah. These two integrals live in 4D, and this integral lives in 2D, that's right. So this is in the same logic that we've seen in some talks yesterday for that. Okay. So basically, you can, and let's compute, for example, box dual with the integrand. Okay, we're going to see how this basically will give generalized unitarity formula. So this is delta 4 on the box cut times a form that's dl4 over, say, some radius square minus L4 square. Some power, 1 plus epsilon, 1 minus epsilon, sorry. And we have to integrate this with our integrand. This delta map is a transpose of the residue map. Again, we lifted the form on like a little circle around our scope. So this thing is integral, so this is like a 5D integral, but this is equal to a 1D integral of dl4 over this. Here I should have put compact support. We take this thing, compact support image of it, wedge the residue, the 4-fold residue of I. So we're taking basically the cut, and then we have to take an intersection. This intersection is a sum at special points L4 equal plus minus R and infinity of basically this 1 over grad times this form. But basically, yeah, the residue of 1 over grad times this form times this thing. And this residue, 1 over grad gives 1 over epsilon for 2 of the special points. So we get 1 over epsilon times the 2 4D residues. Because yeah, the residue where you set this to 0 is when L perp, this thing, remember, is L perp square. So the residue of this twist is the 4-dimensional part of the amplitude. And then there's plus order epsilon from the residue at infinity.
So your form are not rational, right? Because of the fact that you have the minus 2 epsilon, the 2 minus epsilon.
No, yeah, this is okay. Yeah, if you put this in the twist and put grads, then it comes out. Yeah, it's rational. It's algebraic. Yeah, this is algebraic. But as a function of epsilon momentum, maybe you could get s to the epsilon depending on how you normalize things. But basically, yeah. But yeah, so this formula, the 4D limit is the formula of generalized unitarity by BCF, and in general, this gives you the order epsilon correction to that formula. So that's that formula. The more interesting thing I wanted to tell you about, so basically this is just generalized unitarity because it gives you the 4D coefficient, the coefficient in D dimensions, not just 4D. What I wanted to tell you is you can apply the same thing for you can straightforwardly compute bubble dual and so on. Because I've written to you this tree form, and you can compute it, for example, using, you can compute bubble dual intersect with the integral. And you get something that's supported on a 2-cut of the integrand. So basically, this formula, like the fact that all these terms are supported on cuts, explain why generalized unitarity works. The point is that this 2-cut, and then you have to do a 3D integral of the rest of that 3-cut. Yeah, almost done. And this, one way to do it is using fibration. The technology is going to be very similar to what was explained in the previous talk. Basically, once you understand how to do this in the 1D case, you can, which is kind of straightforward, you can apply this and solve the general case. So I can tell you in private how you do it in the 1D case. What I want to tell you here is we're going to briefly sketch one cool formula about symmetrical integration. So when you take the epsilon to 0 limit, this 3D integral similarly is going to localize to where this is going to be. You're going to get a 1 over epsilon from where this is in 4D. So really, this an epsilon to 0, this becomes a 2D integral. But there's something like integral dx dy over some, square root of 1 minus x1 minus y square, some power, which is supposed to make compact support, times you find the integral, you cut. Now, if you look at this, you realize that x squared and y squared are stupid variables. Because, for example, it's obvious you should shift to complex variables where this is 1 minus z bar. And then this is linear in z instead of quadratic. Much better. But those of you who know about twisted cohomology, our space now looks as follows. We only have one as a function of z bar. So if I plot, so z bar and z are independent complex variable in this language. We have a curve like this, and there's a singular point at infinity where these meet. And there's a twist here, epsilon and minus epsilon. And if you look at this fiber here, there's only 2 singular points. And the cohomology where you twist only 2 singular points is empty. So naively, this formula just gives 0. Which is awesome.
But there is the integral.
Yeah, and the thing is that you're going to get something from that point, from that special fiber. And okay, the thing you get from this fiber is a bit subtle to describe. I cannot describe it in 2 minutes, but I will just say briefly that it involves this. The point is that on this fiber, H2 of the fiber, compact support, is not 0 at that special point. And if you, okay, there's some spectral sequence, blah, blah, but basically you can write down a form that looks like delta 2 of Z2 minus A. But you have to localize it around this, inside the circle. I'm going to put delta bar of, sorry, delta 2 of Z bar, delta bar of Z. And then you need patch up to make it close. Exactly the same Matsumoto procedure. And the patch up brings a form that is basically localized here, along this line and ultimately here. You get the following formula, which I'm just going to claim. It's a cool formula. You can verify it in various other ways. So it's a very elementary result. Take x, y, z. Imagine you're on a sphere. Two spheres. X squared plus z squared plus z squared equal 1. Okay? And you're trying to do integral average over a sphere of a polynomial in x and y. Okay? I claim that this is the residue at z equals 0 of the residue at z bar equal infinity of minus arctangent 1 over square root zz bar minus 1 over square root zz bar minus 1 z bar equal infinity times your polynomial of x equals z plus z bar over 2 and y equals z minus z bar over 2y. That's a formula for symmetrical integration. I'm done. So you can check this formula. For example, if you have polynomial 1, you get 1. If you have polynomial x squared, you get 1/3. If you have polynomial x squared, y squared, you get like 1 over 15, and so on. So this is all these trivial numbers you can reproduce by symmetrical integration. This is like integral of cos square in 3D, and so on. You can reproduce it by this formula. So, and this formula is not identical, but it's analogous to a previous formula that people obtained, Akani Ahmed and Cachazo and Kaplan. It's a residue. If you take a large BCSW deformation of that cut, you take a residue at infinite complex momentum, and then a residue in another variable. That's exactly the spirit of this formula. So basically by applying this, so to summarize, yeah, these dual forms, by deciding how you evaluate them, you automatically land on various kind of interesting formulas for the coefficients. You can also take the 4-dimensional limit inside the procedure. The whole procedure you can also do in d dimensions, so we generalize previous results, but yeah. This is the main message. So depending how you, yeah, just if you have if your physics intuition motivates you to take some particularly nice variables that simplify the integral, go ahead and use it. With this formalism, it's going to simplify. And yeah, that is. Yeah, and the other nice things is that all these forms, they live on cuts. So all you have to classify is forms on cuts. The other thing I want to say is that you can define weight of these dual forms, and well, you can ask what dual forms are pure weight, and try to apply this sort of machinery. The sort of interesting thing about the differential equation that these dual forms satisfy is that it's transposed to the usual one. So derivative of bubble dual contains triangle dual and box dual. It's the other way around compared to usual. But if you have a guess, a hunch for what the pure version of bubble dual is, in this case the 2D bubble in 2 dimension, then you apply the procedure that UNS. This is an exercise I haven't done, but if you apply the procedure that UNS described yesterday morning, you should discover the uniform transcendental triangle and box. So this realized the dream of Stefan of generating everything from the simplest one. If you have a hint, if you have a guess for what the pure version of this simpler one is, which It's not obvious, but you can try things. So, thank you.
Thanks to Simon for this very inspiring lecture.
And sorry, I'm going to go for lunch now.
So there were already many questions. Are there any more urgent questions? Yes.
If also for more variable, one can directly get some close formula, because
yeah. I will just say something very briefly. So the reason we get this arctangent as weight 1, the reason we get a dual form of like higher weight is because the bubble has lower weight. So like usual, the dual of the box is like weight 2 in some sense. It's 2 integrals. So dual of the box is like weight 2 times a box which is weight 2. And if you're gonna get a procedure which extracts residue algebraically, the dual of the bubble, which is weight 1, is gonna be a weight 3 function, which is this. So at higher loop, you see that if you're gonna extract a function of weight 2, you're gonna have some dialogue in your procedure effectively. And that would be very nice to see.
No questions, comments? Okay. Well, let's thank again Simon and.
Yes. So we have a couple of hours, or you have a couple of hours, to have lunch. There is, I may suggest, there is a bar just across the bridge here over left toward Hotel Metis, or in case you would like to enjoy a longer walk, you can go toward Via Roma or Prato della Valle, where there are more shops. Okay, and then we will reconvene at 2:30. Thank you.
is there, if we run over, is there any constraints? Okay, so I'll just have 5 minutes already. Yeah, sure.
Misschien la parte più difficile.
Uno, due. Up. What should be up?
No, non penso che vada bene.
Va bene?
Sì, sì. Va bene, va bene.
Funziona? Funziona? Sì, 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 funziona.
Ancora più su.
Speriamo bene. This has been shaded because people should not use it? Or? Yeah, I was wondering why this part is shaded. Oh.
If you have left for talk, then you have to switch this guy on.
Ah, okay.
They can manage to record everything if you slide on the record.
No, I may use that back
then you
more.
have to switch on.
No, it's okay. And there's a star here. Where is this where I'm supposed to be?
There will be repercussions.
There we go.
Right, we're ready to kick off. Very good. So let's start our afternoon session, and we're very happy to have Aula Aluffi talking about characteristic classes within intersection.
Thank you. Thank you very much for the invitation. I confess it's my first time in Padova, although I was born and raised in Italy. And it's a really nice town. I enjoy it a lot and I enjoy the conference. I should confess that I've never computed an amplitude in my life. No? And that's confession number one. Confession number two is that actually the intersection theory I do is not intersection theory you do. So somehow, I guess that's why I'm here. I try to maybe say a few words about intersection theory, the other side of the force, the other side of intersection theory. And my main message will precisely be that there exists such a thing. Yeah, this is my plan. I guess I'm supposed to look at this, right? No, this is more of a colloquium than a research seminar. I will try to give a little bit of the background of intersection theory in algebraic geometry, the way I'm familiar with. And then I will focus on a little corner of that, which is the theory of characteristic classes for singular non-compact algebraic varieties. This should allow me to, so let me stress the non-compact part. That's maybe a little bit of interest to you, since you are computing order characteristics of complements of things. Those are non-compact usually, and this theory is adapted to do that reasonably well. And then these classes will be called CSM classes. When the time comes, you'll see why. And I'll say a few words about these classes for the graph hypersurfaces defined by Zimanczyk polynomials. Okay, that's the plan. And the main message is that there exists a theory called intersection theory, and it has a distinguished history. I will try to kind of give you a little flavor of that. And of course, the obvious question is whether there is a relation between the intersection theory that we do in conventional algebraic geometry and intersection theory that is of use to you. So maybe the main question here is how can I help if there's anything I can do. Okay. That's the plan. I have to also confess that I'm very sleepy. By a rough count, I crossed the Atlantic 200 times, and it doesn't get any easier somehow. The jet lag is a tricky business. So I hope not to fall asleep during the talk. And I've actually been at the talk where the speaker fell asleep. Bianca was kind of famous for doing that. I've witnessed myself. I hope not. By standing, maybe I will not fall asleep. So this is a bit of a history, and it's totally laughable. First of all, it's subjective because it's not the way I view it, and in any case, no, it's 1% of 1% of the real thing. So this goes back to really ancient questions. Algebraic geometry is famous for going back thousands of years, and things that you can recognize as something that sounds like intersection theory is this problem, Apollonius, you may be familiar with this guy. Now, how many circles are tangent to 3 given circles? The answer is 8, and he was able to do a nice construction of that. So answering such questions nowadays would be done with intersection theory. So fast forward to the 1750s, you get the first instance of Bézout's theorem, which is really intersection theory in projective space, and that requires an awareness for what intersection numbers are and what intersection multiplicities are. So although it's hundreds of years ago, still you can see that the people were getting fairly sophisticated about this. In fact, if you go forward a little bit, just a little more than 100 years, you get to Schubert, Hermann Schubert, which at the age of 29 wrote a fantastic book by the title of, what's the title? Does anybody know? Calcul der Abzählender Geometrie or something like that. Right? So something summarizing, among other things, what is now called the Schubert calculus, which is really intersection theory in Grassmannians and beyond. And if you read the book, you will find answers to hundreds of questions in what we call enumerative geometry. You do intersection numbers, we do intersection numbers. Enumerative geometry is computations of numbers. For example, this is a typical question would be how many smooth plane cubic curves in complex projective plane are tangent to 9 lines in general positions. What's the number? Well, in 1872, a very young guy in his thesis proved that there's 33,616. So we are in 1872, which is kind of way back. We cannot read that paper. It's a sequence of 3 or 4 short papers in Canton-Du. And by modern standards, you cannot really make sense of what it says. It would be an excellent project for someone in history of mathematics to figure out what Mr. Maillard was doing in 1872. There was a whole technology that Schubert had talked about and had developed, been developed in the previous decades, using some principle conservation of numbers, things that these people could handle extremely well and seemed extremely reasonable and were absolutely not rigorous. And in fact, just a little further, Hilbert in 1900, as one of his famous problems, asked to put enumerative geometry on solid grounds, make computations in enumerative geometry rigorous. That is not. Hilbert's 15th problem was essentially asking to develop intersection theory, make it a rigorous part of mathematics. And in the 20th century, this was attempted at various level of rigor. Of course, you all know the history of algebraic geometry, and it was guided in the first half of the 20th century by people who understood extremely well what they were doing, but again, by our standards, they were not really working rigorously. So many names can be associated with this kind of efforts. Weil, of course, is super rigorous, but Severi would not. Samuel Seger. Weil was the first person who really put on firm grounds the notion of intersection multiplicity. Samuel did similar work. Chow in the 50s proved a moving lemma, which, if you are coming from homology/cohomology, you think that that should be an extremely natural thing. If you want to intersect 2 objects and they don't intersect nicely, just move one of them so that they intersect nicely, and then do the intersection, and that defines your intersection theory. Why can't we do that? In algebraic geometry, you don't have so much freedom in moving things. Algebraic geometry is very rigid. You can only move things in their, what we call now the rational equivalence class. It's very hard to prove anything about it. So this is a big theorem. The moving lemma is an absolutely non-trivial statement. And indeed, honestly, I don't know the status of this in terms of what we call rigorous mathematics now, because I'm not talking about now 50 or 60 years ago. I'm just talking about 4 or 5 years ago. Joe Harris and David Eisenbud were writing a book in intersection theory. Oh, I should have put this on a slide. It's a beautiful book. It has a beautiful title. Are you familiar with this? This is the title of the book is this. So if you Google Harris 3264, you may find the PDF of the book still available. Obvious question. What is 3264, right? It's the number of conics tangent to 5 conics in general position. So Joe Harris, as you might know, is an extremely strong algebraic geometer, descending from the from these people, Severi, Zariski, and Harris, there's a continuous line between that kind of intuition and his intuition, and one of his tasks in writing this book was to provide an elementary proof of the moving lemma, and he couldn't. And if Joe Harris cannot, in 2015, prove the moving lemma by elementary means, that means it cannot be proved by elementary means. So no, at some point, people realized that they had to move away from that kind of very geometric thinking, and they had to get into the thick of things. Grothendieck, of course, gave a tremendous contribution. Riemann Roch was what he gave his fields matter, and his theory, intersection theory. But the real foundations was really carried out by Fulton and McPherson in the 70s, bordering into the 80s. There's this Bible of intersection theory, from my point of view. It's Fulton's intersection theory that was published in, I think, 1984. And this is completely rigorous. In fact, the only reasonable proof of the moving lemma we know is through the theory of Fulton-McPherson, which is absolutely not in the same spirit as Chow was working. So, no, of course, it's a very well-developed and general theory, but in particular, we know that every algebraic scheme has a Chow group, and you should think of that as a homology in intersection theory, in algebraic geometry. It feels like that. It's a covariant functor. It moves nicely across proper maps. And if you are non-singular, if your variety is non-singular, then this group has a well-defined intersection product, which makes it into something that looks like cohomology. And there are many situations, Grassmannian's projective space may ignore, in which homology and Chow are the same theory. So in this talk, I will really not talk about Chow at all, Chow group, because I think it will not add anything to what I'm going to say. Yeah, I had a couple of remarks. I mean, if you think, no, how can you do this? And you are familiar with intersection theory the way I've seen in this meeting, then you probably think there must be some clever way of putting differential forms together to obtain numbers or intersections. And that's not the case. Differential forms are not part of the theory. As I mentioned, Chow's moving lemma is also not an ingredient in Fulton-McPherson. And the Chow group is actually not for special varieties, maybe not for the varieties you may care about, but it is in general tremendously finer than homology. For example, oh, this is a terrible mistake, right? Let's see. Oh, so what's a good example? Elliptic curves. No, if you look at dimension 0 or an elliptic curve, no, H0 is not very interesting because they are connected, while the Chow group is tremendously big. It's uncountably generated. No? So you see, no, it's a very, very fine theory, but again, in this talk, that will not really play a role. But just to stress that there are substantial differences between what Fulton and McPherson did in developing intersection theory and what you might be used to thinking in terms of the calculus superform. I think I had a nice, yes. So I will just mention what the ingredients are. And this is a typical situation in Fulton-McPherson intersection theory. Cycle just means, take subvarieties. You have two subvarieties in a variety V. I'm not asking V to be non-singular, but I'm asking the first of the two subvarieties to be nicely embedded in V, which means it has a nice normal bundle. No, locally, it's given as a complete intersection, something like that. While I put no requirement on Y. And then I do something magical. I don't move anything, but I deform things. I deform the embedding of, I probably should not even attempt to do this, but if this is V and this is X, X is nicely embedded, Y may not be so nicely embedded, who knows. I deform the situation to the situation in which V is replaced by the normal bundle, so something very straight of X and V. X is replaced by the zero section, and Y is replaced by a cone, which in this picture might look like this. There's a deformation that takes you from here to there, and Fulton exploits it to reduce this intersection problem to an intersection problem like this. And this is very standard. Normal bundles are nice. I mean, the vector bundles are nice. Zero sections are super nice in vector bundles, and cones are, to some extent, under control. Once you do that, now, as my slide doesn't promise, oh, I see. Please go back to the slide. There we go. As in my slides, you can see this deformation. Yeah, these are the ingredients. what you get is a problem that you can study on its own, and your intersection product will be a suitable cocktail of Chern classes and Segre classes. I'm emphasizing Segre because that's something I care tremendously much about. In any concrete problem I've encountered myself, the Chern class was never a problem, but the Segre class, which is what takes care of this cone, that is super subtle. And I keep trying to find ways to make computation of Segre classes more reasonable. But that's a different talk. Okay, so if you have this, then all expected probability of the intersection theory, that as you might expect from your experience with intersection theory, can be proven from these definitions. So for example, the 33,616 cubics turned out to be indeed 33,616. That's my PhD thesis, as it happens. It was done exactly at the same time by Kleiman and Spicer too. And many, many more innovative questions were answered. In the 90s, there was a very substantial application of this theory to modular spaces, and this was mentioned already today, and probably yesterday, so this will not tell you much that you may not be familiar with. There's something called Faber's conjecture. Faber is Karl Faber, and now he works in Utrecht. On the tautological ring, that's a ring associated with the Chow ring or modular space, genus G curves, and punctures, and parts of them are still open. And they are extremely subtle. In fact, if you try to generalize them a little bit, you get wrong statements, and Ursula Tomasi is in the audience and is in Padova, so that's whom you should ask to talk about these things. I'm definitely not an expert, but she is. Again, in the 90s, Witten's conjectures on intersection numbers of the modular space were proven by Kontsevich, and that's, I think, the main motivation for Kontsevich fields Mellor. By the way, yes, as I was reading a little bit of the papers that you people write, I run into interest in M0, and well, Sean Keel, a student of Fulton, has a very nice paper on intersection theory of M0 and bar. So if you're familiar with it, excellent. If you're not, you may want to look into it. It's in the transactions, you can find it very easily. There's a very nice paper by Manin, dating back to '94, called Generating Functions in Algebraic Geometry, and among other things, you get Betti numbers for M0 and bar. There's nice generating functions for the kind of things. I'm just implying that there was a lot of activity in this field in the 90s. In fact, there was this tremendous surprise for mathematicians, and this was mentioned today, this morning, at the Yanko, right? A computation by Candelas, Delos, Green, and Parkus of the number of cubics in the quintic threefold, exactly at the same time when Ellingshausen and Strömer were doing it in mathematics, and the two numbers were not the same. And this is like 25 years ago. So I can tell you that the mathematicians will say, these physicists, okay, how can they possibly imagine they compute with it? They don't get our number, they are wrong, right? And of course, the physicists were right. It was kind of embarrassing, but and not only that, I mean, mathematicians could produce the number of lines of conics and after some corrections of cubics, and that was it. The physicists would give this generating series in which the coefficient of q to the 100 would be the number of degree 100 curves indeed. So it was clear that the physicists had something to teach to the mathematicians, and that down the road became, this is a gross oversimplification, quantum cohomology. And there are names associated with that, Fulton again, Pandaripanda. Graeber, who's visiting Padova this semester, so again, if you want to hear about this, invite Tom Graeber to talk to you. Okonkov, Behrendt, Van Teki, there's many more, of course. And then there are developments. Intersection theory is now done in stacks. There's equivariant intersection theory. I want to mention this because some computations in equivariant intersection theory look a lot like the kind of computations I've seen you talk about. Typically, you have a group acting on a variety. You want to compute, for example, a Chern class or some kind of intersection theoretic object. And the action of the group allows you to localize this so that you look at the fixed points of the action. Each fixed point will give a contribution. If you do explicit computation, these contributions will be nice, complicated rational functions, and then magically, once you put them together, you get a very neat answer. And doesn't that sound familiar? I mean, I've seen this happen in your talks. So I'm suggesting that there may be a connection there. And more, I mean, this is also connected with physics, Thomas invariance, Schubert calculus as a modern version. And then in red, because that's the next topic, among other things, people have thought about characteristic classes for singular varieties, and that's what I want to talk about next. Any question? Any complaints? Yes. So in fact, if you're intersection theory, I claim, is a field. It has an item in the mathematical reviews. And if you Google that, you get about 1,000 papers. At any given time, there's about 30 papers pending. So it is a rather, maybe not super big, but rather active subfield of algebraic geometry. Okay, so this is one topic that I just personally care a lot about. And again, I like these names. This goes back to something that Lee and Grothendieck proposed back in the 60s, that Maria and Schwarz did in the 60s. And then there are more names: Mather, McPherson, Fulton again, Johnson, Brasileiro, Yukura. That takes you to the 80s. I did work on this since the 90s, so did Parzyński, Progress, Sherman, many names can be associated with this. I don't know if any of them sound familiar to you. So the prototype is the observation that vector bundles have Chern classes, and another gross oversimplification, but the ith Chern class of E is the obstruction to finding a certain number of linearly independent global sections in the bundle. Or if you want, yeah, I mean, the one I will care about is for a smooth, compact variety, you have the tangent bundle, and I want to consider the total Chern class, the sum of those CIs, for this particular bundle. So the components of this class tells you how far you are from defining global frames of vector fields in B. And by the way, you could talk about the cotangent bundle instead of the tangent bundle. That will not make any difference. It's obstruction to find the linear independent differential forms on your variety. So this is has been around for a long time. It's very well studied, and it's an important invariant. For example, the degree 0, the dimension 0 part of this class is the Euler characteristic. It's the obstruction to finding a non-vanishing vector field. That's due to Poincare, the Euler characteristic. Other things that you can see from the Chern class, for example, you can tell whether your variety is a Calabi-Yau by looking at the first component of this class, because it's negative the canonical bundle. Poincare I mentioned is the fact that the degree by this integral, I don't really mean an integral, but I mean picking up the degree of the zero-dimensional class in the class I'm writing over here. That is the topological Euler characteristic, which apparently people care about. So the question that goes floating around is, what is the right analog of this class? But if you give up the non-singular / compact assumption, what if your variety is singular? What if it is non-compact? Can you still come up with some kind of invariant that will have the same type of information? So for example, M0n, does it have some kind of total Chern class? So the first time I looked at this, there was a naive answer still. No, you can just, if your variety is singular, well, instead of the tangent bundle, use something else. Use some kind of naturally defined bundle. For example, the sheaf of differential forms is defined for every scheme. Can't I use that to define a class like this? And the short answer is that you cannot do that, or at least it doesn't really lead to a good theory. Korean sheaves, which is what omega 1 would be in general, don't really have Chern classes, and there are ways to fix that, and it leads to important classes called Chern Mather classes. But it doesn't quite do what I need to do. For example, in the non-compact case, I would lose too much information. I would not be able to extract the Euler characteristic from this class. So we're not going to do this. We need something a little less naive. And by the way, my time is running, but I want to mention that again, as physicists, you probably are very familiar with this, more familiar than I. There was a proposal for Euler numbers of quotients, varieties with all different singularities. This was proposed more than 30 years ago by Dixon, Harvey, Buff, and Witten. Batilev generalized this to a notion of stringy Euler number, and that has a Chern class associated with it. So there is a class whose degree is the stringy Euler number, just in case you run into that. That's an interesting story, but it's not what I want to do, because again, I want to focus a little bit on something that will give me information even if it is not compact, and that class doesn't do it. So let me describe something that is more than 50 years old, but somehow it's not as famous as it should be, I believe. It's an idea that goes back to Grothendieck. There's an interesting history about it, but this is not the place for that. And it requires a bit of machinery. So, as they say at the dentist, this will cause a little bit of discomfort, maybe if you're not used to thinking in these terms. But so take a group, the group of integer-valued constructible functions. So those are things that you can write as a sum of indicator functions, a function 1 that is 1 if you are on W, if you follow the notation, and it's 0 if you're not on W. And just take arbitrary linear combination of those with integer coefficients. Okay, finite linear combinations. So this may not look like a very interesting object because it's just taking some varieties, giving them some weights, possibly negative, possibly positive. So if you're used to thinking in a certain way, it's just a group of cycles, algebraic cycles on V. But I'm going to do something that is not directly related with cycles, and that is I'm going to make a functor out of that in what might seem an unusual way. And notice I restrict myself to complex projective varieties, so I'm allowed to use things like the topological error characteristic. Let me tell you what happens if you have a proper map from a variety to another. I claim that you get a push forward at the level of constructible functions. And how do you define that? Well, generators here are indicator functions for subvarieties, so I pick a subvariety of x. And the result should be a function of y, so I pick a point of y, and I have to tell you what this number should be. What is the push forward of the function 1 sub w, and it is defined to be the Euler characteristic of the fiber. Topological Euler characteristic, something that everybody's familiar with. It's not hard to check that this is indeed a functorial prescription. That is, if you compose two proper functions and take the push forward, in a sense, that's the same as composing the push forwards. And there's another covariant functor around, which is homology. This is right because that's what I want you to focus on. Chow is also a nice covariant functor, but pick homology. That's also a functor from varieties to abelian groups. So now you have two functors, two covariant functors from a category to another category, and as mathematicians, you should, or I should, we should ask whether there's a way to connect them. And that's what became known as a question posed by Deligne and Grothendieck. Is there a natural transformation that is a system of commutative diagrams, essentially, which links these two functors? So that if V is no singular variety, then the image of the indicator function of V is the Chern class. Questions? You should complain if what I say sounds mysterious. This is, I'm trying to claim that this is a natural question in the context. You have two functors, you have to compare them, and then the genius of these two guys was to require that the simplest function here would go to the most interesting class over there, 4 non-singular varieties. So this was around for a little while, and then McPherson came around in about 10 years after this was posed and proved that this is indeed the case. So there is such a natural transformation. Yes, please. Yeah. In McPherson's paper, that would be smooth. Sorry, would be complex projective varieties, and the theory has been pushed beyond that. For example, Kennedy and others, I'm also partly responsible for that, do this over arbitrary algebraically closed fields of characteristic 0, and even the compactness hypothesis is gone. So we can do this. We don't even need to just look at proper maps. It works for very, very generally. But that's a good question, because since I've been advertising that this should work for no compact things, I'm kind of doing something a little strange, because this theory is defined on compact varieties at this stage. So please appreciate this. It's a very, this is maybe the main thing in my talk. There exists a functorial theory. Functorial is good, right? Even if you're not used to thinking about functorial all the time, but you're happy if something is functorial, of Chern classes, something that generalizes the familiar notion of Chern class from non-singular varieties, that works for arbitrarily singular projective varieties. It satisfies the same combinatorial properties as the topological characteristic. So it's a powerful observation. This is a beautiful theorem. So now if you fix a projective, for example, Pn, and then look at any locally closed subset, for example, an affine variety within Pn, it does not need to be compact. Then I can define a class. The class is called the Schwarz Macpherson class by assigning to x the value of this natural transformation at the indicator function 1x. Now, the indicator function is the simplest function. Right? This should be a very simple object. It's the most natural choice of the function, and then you have this natural transformation. What could be more natural than that? So this is, don't even know if I'm pointing this out. Probably not, but the point is that if I plug a non-singular variety in place of x, what I get out is the ordinary Chern class of the tangent bundle. So I've managed to find an analog for the Chern class of the tangent bundle, even if the tangent bundle is not there. And here I'm making the point that this can be done actually in Charles, so you don't need to, it's a finite theory in Charles. Okay, so for example, there exists a well-defined class, the Chern-Schwarz-Macpherson class of M0n in the homology of M0n bar. And I think nobody knows what the class is. And every now and then I get the idea that I should compute it, but I've never gone very far with that. I think it would be a very interesting object to study. So I want to give you a little bit of a feel for what this class does and how you compute it very quickly. I claim it has the same combinatorial properties as the Euler characteristic. For example, you have inclusion and exclusion. If you have two subvarieties of a fixed variety, then you get this nice, I call it inclusion and exclusion because in the US, when we teach combinatorics to undergraduates, we have this principle of inclusion and exclusion that tells you that the number of elements in the union of two sets is the sum of the elements in here, plus the elements in here, minus the elements in the intersection. And you see that's exactly what this class is doing. So there are formulas for this that again call back to the same ingredients that define intersection theory. There's formulas in terms of Chern classes and set classes for these objects. And in fact, I was able to put together a procedure that runs on Macaulay 2 that will compute this class if you give me the ideal of a subscheme of projective space. So I'm trying to point out that these things can be computed. And they have to do with logarithmic differentials, which you people seem to care about. If you look at the complement of a simple number crossing divisor, then the CSM class of that is the same information as the Chern class of the dual of the logarithmic forms on V. And in fact, this generalizes to more general, not arbitrary, free divisors, the result of also a beautiful theorem. It's not hard to see that if you are within Pn, then the degrees of the components of this class carry the same information. This is not an equal sign because they are not the same, but they have the same information as the Euler characteristic of general linear sections of X. So to some extent, they are geometric objects. Let me give you a hint of why functoriality is so nice. Out of functoriality, you get a Poincare-Hoff. Functoriality means that these kind of diagrams commute. So if you start from a constructible function on V, carry it over to H star, apply this natural transformation for the constant function, you should get some identity. And the identity you get is Poincare-Hoff. If X is non-singular, this is saying that the Euler characteristic of X is the degree of the Chern class of X. But this generalizes Poincare-Hoff to arbitrary singular and arbitrary non-compact varieties. How's my time? I started a little late, so I think I still have a few minutes. Okay, CSM has been studied for decades at this point, very intense in the last 20 years or so. Rosino have a paper on the Journal of the MS on the CSM class for degeneracy loci. That's an umbrella that covers many, many interesting cases in geometry. Toric varieties are very easy to deal with in terms of CSM class. If you are familiar with toric varieties, each orbit, take the closure of each orbit, that gives you a cycle within the toric variety. Take the sum of those with coefficients 1, that gives you the CSM class. So, what could be simpler than that? And right now, actually, we're working very hard to figure out the theory of CSM classes and more general objects on sugar varieties in flag manifolds, and that's a work in progress to some extent. There have been generalization. There's something called motivic Chern classes. There's the covariant version of CSM classes, and so on and so forth. And this has been very active. Okay, more time for complaints, questions? What I want to do in the next 9 slides, I'm always very happy when the speakers put the number of slides so I know where I am in the talk. In the next 8 minutes and 9 slides, I will say something about graph hypersurfaces, because that's the closest that I've ever come to working with something that sounds a little like what you people are doing. Of course, I'm totally ignorant about the physics side of the story, and I beg for your forgiveness already. But to start with the graph, and the motivation is you want to look at contributions that the graph may give to the computation of a Feynman integral. The edges correspond to variables, and there's a polynomial that you can look at. And I think this is called the Kirchhoff, or the second Zemancic polynomial. It's a specialization of the Tott polynomial. It's just the sum. You're probably more familiar with this than I. You take the sum over all maximum spanning forests of G, if G is connected just spanning trees, and you take the product of the variables corresponding to edges not in the tree. That gives you a polynomial. For example, here's my favorite case. You start with the banana. The spanning trees, you see them, and there's 1, 2, and 3, and the edges that are not in the spanning tree are just choices of 2 of the variables. So, super explicit polynomial. This is homogeneous and defines a certain hypersurface in Pn-1, so that's what I call the graph hypersurface. Turns out actually it's sometimes better to consider the cone over this in AN, but maybe that will not play a role. The degree is the number of loops in your graph, and this is irreducible if and only if you cannot split the graph as a disjoint union of 2 graphs. So at some point we wanted to understand this, and the motivation, again, this is beyond my pay grade to some extent, it's above my head, but there were hundreds of computations suggesting that contributions of graphs to Feynman amplitudes may be very special kind of numbers, and this was mentioned yesterday to some extent. Multiple zeta values. For a while this was kind of mysterious, I suppose. It had been verified for all graphs up to a tremendous number of edges, but still small by all measures, and it just, at some point, was realized that this was not going to be the case for all graphs, and Francis Brown is about the world expert on this, so he will be the right person to talk about it. In any case, as was mentioned already, the Feynman contribution of a graph is a period of the complement of the hypersurface, and these are controlled by the motive of the hypersurface. So what is the motive, by the way? It's some kind of universal error characteristic. We can talk about it, but that would be taking too much time. In fact, I see my time is running out, so let me accelerate a bit. But I'm still trying to give the motivation. So this fact about multiple zeta values was related to qualities of this motive. It was a conjecture that, for example, if you count the number of points over a finite field of these hypersurfaces, that number should be a polynomial in the number of points in the field. So the question was, is the motive of such a hypersurface, or rather its complement, a so-called mixed state motive? And I just told you that this is actually not true. It was not true. Nevertheless, it generated questions, right? For which graphs is it true? And what kind of operations of a graph would preserve this property? And more broadly, study properties of a graph which only depend on this hypersurface. At some point, this name was floating around algebra geometric Feynman rules. In a sense, these are just homomorphism from an algebra of graphs to your favorite ring that should only depend on X and G. And CSM, this class I talked about, is also a generalized error characteristic. For some reason, it does not depend on the motive, and ask me why if you care. Anyway, this I took as a motivation to study the CSM class of the graph hypersurface. Can be used to construct one of these homomorphisms from graphs to some interesting ring. So number one, and for certain easy graphs, and this is joint work with Matilde Marcoli, whom some of you may know. For simple graphs, this could be computed very explicitly. We don't need to get into that. In any case, I will not tell you anything about the proof. It really relies on the functoriality of CSM classes and constructions that have to do with this hypersurfaces, maybe the more here, I think I have a line about that, is that the work needed to compute the motive, which is this high-level object, can be retooled to say something about the CSM class. So in particular, by the way, this is something that you may disprove, you may no more example deny. For these banana graphs, you see the Euler characteristic is plus or minus 1, right? And you care about the Euler characteristic of the complement of these kind of hypersurfaces. Sorry, yes. I didn't write it correctly. What I meant was the Euler characteristic of the complement of the hypersurface corresponding to the graph. So the kind of Euler characteristic that I've heard you talk about. And I've never seen a graph for which this is not 0 or plus or minus 1. If you know more examples, I think Francis will be the right person to come up with an example that is not the case. All the examples I've been able to compute, the Euler characteristic of the complement of the hypersurface was always 0 or plus or minus 1. And that's kind of striking cause for a proof if it is true on a content example. Let me just say a word about a companion algebra geometric final rule. This formula, which if you're like me at the talk you cannot parse, but you can take the CSM class and then cook up a polynomial that has the same information. Well, it is a homomorphism of the algebra of graphs. So it satisfies the basic property that we require of these algebra geometric final rules. Its target is polynomials. This is a polynomial. You can compute it in many cases. The corresponding propagator, if that is the right term, is 1 plus t. And properties of these, I can just list a few. We don't need to stare at all of them. Let's see. It's monic. Coefficient of t minus 1 is easy. Maybe this one is the one that you might care most about. The Euler characteristic of the complement is the first derivative of this polynomial evaluated as 0. So to some extent, this polynomial has some information you may care about. And then you can try and prove theorems about this polynomial, and this is the most sophisticated result I ever got about it, and I'm very unhappy about it, which is why I more or less stopped working on this, because of these unfortunate technical conditions. If you have an edge of the graph, then I have a way to relate the graphs you get by doubling the edge, leaving the edge alone, removing the edge, or contracting the edge. Now, this is a prototype for a deletion contraction formula, which is the kind of things you expect in handling with graphs. But these unfortunate technical conditions are really unfortunate, so that limits the scope of this kind of formulas a lot. But no, there's a hint that this polynomial can actually be computed in practice and satisfy some nice results. Okay, so one question is, can you throw away those conditions? I couldn't, and if you're interested, you can look up my paper and see if you can get rid of them. And there are now natural questions, and my time is definitely up. Can you construct a CSM class in twisted cohomology? Really, this is a question about how functorial is the cohomology you care about. No. Your twisted cohomology, does it have a nice functoriality that they can start from to try to construct a theory of CSM classes in twisted cohomology? And if there's such a theory, then is there a twisted algebra geometric final rules? And the reason why I would care is that maybe then relations among these classes would correspond to relations of the corresponding amplitudes, which is a speculation without any shred of evidence whatsoever, but it's a question. Okay, so thanks for your attention. Sorry for
Thank you very much for this interesting talk. We have a few moments for questions. Just one already. You want to go?
What if any are the connections between the CSM or the graph surface and the class and the property?
Yes.
Class and K0.
Yeah, in a sense, let me answer that by why is this not coming from the... so the question is, if this was recorded, whether there's a relation between the class and the growth ring, which I've not talked about, that is what I hinted at by saying motive, and the CSM class. If there were a nice relation that would allow me to go from one to the other, that would be done. The growth ring is universal with respect to Euler characteristic, and the CSM class has an Euler characteristic flavor, so you would expect there should be a homomorphism from the growth ring that determines the CSM class, and that doesn't happen because the universality of the growth ring refers to Euler characteristic with a fixed target, while the CSM class has moving target. The target of the CSM class is the homology of the variety of working with, and that moves. So Now, there are situations in which you can establish an easy connection. For example, if you're just dealing with hyperplanar arrangements or arrangements of linear subspaces in projective space, then the information is the same. So for example, I use this to get out of CSM class the chromatic number of a graph, because you can interpret that as the Euler characteristic, more or less, of the complement of the corresponding hyperplanar arrangement. Things like that. But yeah, excellent question, but unfortunately the answer is no.
Sorry, microphone.
Okay. So you computed the Euler characteristic of the graph hypersurface, but you took one of the. There are two graph polynomial you can construct from a Feynman graph, right?
Right. I've only dealt with this polynomial. I've never looked at the other one.
Yeah. So the other one is really where the physics is, because the Euler characteristic counts the number of what we call master integrals. So in particular, the Euler characteristic is non-zero. I mean, is different from 0 and plus or minus 1. I mean, it really knows about the geometry that is beyond that.
Well, that's encouraging me to work on that, or that should be looked at, but I've never worked with it. Sorry.
So well, you didn't look at this one. Is this for technical reason, or is it? No,
yeah, many other things that
okay.
My fault. But thanks for suggesting that. Certainly sensible question.
So I wanted to ask about your unfortunate technical assumptions, and my hearing isn't very good, so I didn't hear whether or not it's unfortunate that you had to make technical assumptions to prove it, or unfortunately there are counterexamples. Which is the case? Are there counterexamples?
I think it's the former, but this is work that goes back almost 10 years, and I've tried to forget it to some extent because it was a disappointment. The condition is, in fact, I will not even be able to reproduce it right now, but it is a funny condition that is not always satisfied. The question is whether that condition is necessary for the result, and I don't think I know the answer to this second question.
So
I have counterexamples to the condition, but not to the consequence of the condition.
Yeah, right. So
and the condition is, it's kind of funny. It's requiring essentially, oh my goodness, it was easy to state when one remembered it, but it had to do with whether the derivative, the partials of the polynomial that defines the graph hypersurface would be in the ideal generated by deletions or something like that. So something that seems totally unlikely, and then you try for 5 graphs and it works all the time. And then, no, at the 6th graph you'll find a counterexample. So there are situations in which you can guarantee that that is the case, and that's what led to that.
You see, I want to report this to Karen Yates, who's an expert on the combinatorics of the first Zemanzik thing.
That,
so I want to be able to tell her whether or not there's a counterexample to that as a conjecture.
Karen Yates and a postdoc and a student of hers had a paper on one of these conditions where they studied more carefully than I ever did, and she will be able to answer your question. But I don't know if that is a counterexample to the formula I put in the book. That's a different story.
Thank you.
So I don't see any more other questions. We can thank Paolo again.
Thank you. Of course. No, I'll keep it. Are you going to handle this? It's easy.
Stefan, you can all these in your pocket.
So next talk is from Stefan Weinzierl from Mainz, who will talk to us about scattering forms and the CFY representation.
So thank you for inviting me to this conference. So I'm a little bit off topic because I won't speak about Feynman integrals. I will just speak about Feynman tree diagrams. But to be fair, instead of speaking about one diagram, I will speak about the sum of all diagrams which contribute to an amplitude for any number of external legs. So instead of considering basically really the sum of all Feynman diagrams, the game will be to rewrite this sum as a single formula at the expense of introducing an integral. So we're back to integrals. And then basically I will try to see basically how various pieces which exist in the literature fit nicely together. So that is basically work done with Alexander and Leonardo is also here in the audience. So, and how is this? Okay. That's a little bit more detailed outline, basically. I will consider 3 examples of theories which a priori have nothing to do, and I will like to show you that they are related basically in a very nice way. And then basically I review basically a few of ingredients, which is now standard technology, and in the end basically we come basically to see basically what is essentially the geometry of 3 amplitudes. So the 3 players are the B-adjoint scalar theory, Young-Mills theory, and gravity. So let's start basically with the middle one, basically Young-Mills theory. And as I said before, basically I will consider arbitrary number of external particles, so that will be denoted n in the following. So Young-Mills theory basically it's given by a Lagrangian, and basically if we write down the tree amplitude, it obviously depends on the momentum of the external particles and basically on the polarization, the spin. And then there's a standard procedure that basically we can rewrite it as a linear combination where we take out explicitly the color factors, the SUN or UN color factors. They always can be combined into traces, and basically the color matrices can appear in different orders. So this defines a cyclic order, and the coefficient of what multiplies this color structure we call a partial amplitude. So also since this partial amplitude depends on some cyclic order, and basically it's just an order how you label 1 to n in a cyclic way. So basically the important message is basically our amplitude depends on the momentum, a cyclic order, and basically the spins of the particle. And we can calculate it from Feynman rules, so this is really the straightforward dumb way to do it. If we are basically in the cyclic ordered amplitude, we have a little bit simpler Feynman rules, so basically the four-clue vertex is a little bit simpler than usual. Yeah, okay, so that's basically just the message. You can compute these things if you really want. Then the second player is the B-adjoint scalar theory. It's given by this Lagrange density. It's a scalar particle which basically lives in 2 gauge groups, let's say G and G tilde. So it has 2 gauge indices or 2 color indices. And then you can play the same game as a color decomposition, basically rewrite everything in traces of 1 gauge group and something else in traces of the other gauge group. So you now have 2 orders in these traces. So basically the original thing, it's a scalar theory, spin 0, so it does not depend on any spins, so just on the momentum. If you now do this double decomposition, it depends on 2 cyclic orders. And then basically, if you fix now these 2 cyclic orders, which graph contribute basically to this double order amplitude, basically it's just the graph which you can bring to a flip basically into the corresponding other order. For instance, this is order 1, 2, 3, 4, 5. Now look at the red vertex here. If I exchange 2 lines at this vertex, I get to this graph, and now the cyclic order is 1, 4, 2, 3, 5. And basically it will contribute basically to the double cyclic ordered amplitude with this 1 order and the second order, that one. Yeah. And then basically the Feynman rules basically are rather simple. It's just a scalar theory, so rather trivial. And the last one is gravity, basically perturbative gravity, where you expand around flat Minkowski metric. So basically this is a Minkowski matrix. This is a small perturbation. Kappa is assumed to be small. And then basically you just have the standard Einstein-Hilbert action. And basically what you get here is an infinite tower in your Lagrangian, if you order it by the fields of the graviton here, this H is a graviton field, because you get basically an infinite number here, basically from the square root of the determinant, and also from expanding basically the scalar curvature. But again, you can treat it basically as a perturbative theory, and basically you get basically Feynman rules, basically you get something for the propagator. Now a graviton has spin 2, you can describe a spin 2 as a product of two spin 1 polarization vectors, something like that. You can work out expression for the vertices. I didn't write it down because they are rather long, and plus in addition you have 5 graviton vertices and so on. And obviously the graviton amplitude depends on your momenta, and basically let me write basically the spin 2 polarization tensors as a product of spin 1 polarization vectors. So I say I collect all the ones for basically the first entry in epsilon and the second entry in epsilon tilde. So basically it depends basically on 2 copies of spin 1 polarization vectors. So in principle, all the 3 theories I introduced here, you can be computed from Feynman diagrams. It's a little bit boring, it's tedious, it's a lot of work. So for the scalar theory, it's still feasible to write down a compact formula in this way here, but I didn't bother to do that for the other 2 theories. Now, let me review some recent developments. I would like to start with Jacobi-like relations. So what is this? Basically, you know from a Lie algebra, SU3, SUN, UN, basically you have basically this Jacobi relation here. You can rewrite it in terms of structure constant, then it looks like that. Or you can rewrite it basically graphically, basically where you say each vertex is basically corresponds to a structure constant and repeated indices are summed over. Then you get basically these 3 diagrams, and you see basically it's always the same diagram, it's just the labeling of the upper legs which is different, and the Jacobi identity simply tells you that the sum of the 3 vanishes, which is basically exactly this equation here, the second one. Now, if you look at Young-Mills theory, basically, of course you have 4 Coulomb vertices. You can always rewrite it in a way that you just have 3 valent vertices by just saying insert a fake propagator here, basically p squared over p squared, which is 1, and basically you can either do it in that way or either in that way, just to make sure that the sum gives the original vertex. There's some arbitrary way of splitting that thing, so it's not unique, but you can rewrite it basically in terms of 3 vertices only. So basically you can rewrite your Young-Mills amplitude as a sum over graphs, 3 valent graphs with 3 valent vertices only. So you get some denominators as in a scalar theory, and then you get some numerators. And you would get also some numerators from standard Feynman rules with just some arbitrary splitting of the 4 Coulomb vertex. Now, BCJ from Byrne, Carrasco, Johansson says you can choose, there exist numerators basically whenever you have basically 3 graphs which look like that, basically with a labeling like that you can choose numerators which satisfy this Jacobi identity. They don't come out naturally from standard Feynman rules, but they exist. And you can solve for them basically with standard linear algebra tools. If you have that, basically you can do the following. If you have basically something like that, and assume the Jacobi identity and antisymmetry of 3 Coulomb vertices, which is always guaranteed, you basically can bring this graph down to a linear combination of those graphs. And if you do that repeatedly, basically, you can fix basically a line 1 and n, and basically reduce any side branches, which are again trees, just basically to this simple thing here. So these graphs here are called multiperipheral graphs. I think that's the name Victorial gave them. I will use basically here the name comp graph for obvious reasons. So basically, then double copy or color kinematics duality is the statement that once you brought your Young-Mills amplitude in a form where these kinematic numerators satisfy Jacobi relations, you straightforwardly can calculate the graviton amplitude by just squaring that one and erasing the color factor. So this is basically just another copy of this kinematic numerators. And of course, basically you get the p-adjoint scalar amplitude by erasing the kinematic numerators and putting in another color numerator there. And I should also mention that you can calculate these BCGA numerators also from an effective Lagrangian, which agrees with the standard Lagrangian, basically in the terms which have 2, 3, and 4 fields, but in addition has an infinite tower of more fields, and basically this tower of more fields is a complicated zero due to color, but if you keep it basically and treat it as a formal expression, you derive Feynman roots from it, they generate then the BCGA numerators for you. So let's come to the CHY formalism, and let's come to integrals. Let's introduce some auxiliary space, which is basically you start from a Riemann sphere and mark n points on that, and then you mod out Möbius transformation. So that space is called the model space of a Riemann sphere with n marked points. It's known it's of dimension n minus 3 because you can use Möbius transformation to fix 3 points at any location you like, usually 0, 1, and infinity. Then basically label basically the coordinates on that space by z, and basically each external particle gets a coordinate z, and then just consider these functions here, basically where basically here I have the momenta, and here's this auxiliary coordinates z. And then basically call basically where these functions I, fi basically are 0, calls them the scattering equations. So you have n of them basically. This I can be 1 to n. And you can convince yourself that only n minus 3 are independent. And basically then the question is, given the external momenta, what values of that satisfy these conditions? Basically, we are interested in solutions of these scattering equations, not just if you have one solution and you Möbius transform them, it's again a solution. This is not interesting. Basically, we are interested in basically the number of solutions which are not related by Möbius transformation. This is a finite number, and it's n minus 3 factorial. We call them n minus 3 factorial inequivalent solutions. Then Cachasso, He, and Yuan, they found out basically that you can write basically these 3 amplitudes I talked about as basically integrals, contour integrals, which localize on the solutions of the scattering equations by, it's always the same measure, and then you have 2 factors, one color factor and one polarization factor, as we can call it. And then it just depends if you have 2 color factors, 2 cyclic factors, 1 cyclic factor, 1 polarization factor, so 2 then, and then you either get the p-adjoint scalar, Young-Mills, or gravity. Now, I mentioned basically these contour integrals here, basically, they localize on the solutions of the scattering equations. These scattering equations, they are rational functions in that you can equivalently basically write them as a polynomial system of equations, and then you can think about the ideal generated by this polynomial system and think about a global residue, and it turns out basically that all these contour integrals basically are just global residues, and that was shown by Young and collaborator Matz. Now, the question is, what are these functions entering there? Basically, it's the first one. The cyclic factor is rather simple. It's given here. Basically, you have some cyclic order, you have your Z variables, and then basically just the differences appear as they appear in the cyclic order. So this is a rather simple factor. The other one, the polarization factor, basically encodes the information about the polarizations and the helicities. There's one way to define it, and basically there is some freedom how to define it, because you can, if you have one definition, since it's a global residue, you can add to that basically anything you like which vanishes on the solution of the scattering equations. It still gives the correct answer. Okay? So let me just give you the original definition, which is basically due to a reduced Pfaffian. So this is basically, you construct a certain matrix, 2n by 2n, basically. That basically is a upper left part, basically is just given more or less something like you've seen in the scattering equations. the lower right part, basically, you replace basically the momenta by the polarization vectors, and basically the off-diagonal part, you replace one momentum by one polarization vector. It's an antisymmetric matrix, and then you can basically calculate the Pfaffian for it. The Pfaffian vanishes, and then you say, okay, maybe I erase two basically lines and columns from basically the first part here, and basically two lines here, and calculate then the Pfaffian. That's called the reduced Pfaffian, and then it's non-zero. And you can show basically that this reduced Pfaffian basically is independent basically of what lines and columns you delete if you're on the solutions of the scattering equations, if your external momenta are onshore, which we assume they are, and if your polarizations are transverse, which we assume they are. One sentence about KLT relations. This is the oldest thing, basically, which relates the three amplitudes. And basically, first of all, you can count in Yang-Mills theory, basically, how many amplitudes are there. And basically, of course, there are n factorial external orderings, but they have to be cyclic invariants because they multiply the trace, so they're just n minus 1 factorial. Then you can use antisymmetry of the vertices to reduce them to n minus 2 factorial, and then the Jacobi relation reduce them to the n minus 3 factorials. So basically you have basically the independent partial amplitudes are n minus 3 factorial. And you can do that basically for the B adjoint scalar amplitudes, basically that your two basically cyclic orderings runs basically about n minus 3 factorials. You fix 3 legs basically and let the other n minus 3 basically run through all permutations, and that defines you a huge matrix of dimension n minus 3 factorial times n minus 3 factorial. This matrix is invertible, and then basically you call the inverse of this matrix S. So, and that is basically what we now call the KLT matrix, and then basically you get the gravity amplitude if you think about this Yang-Mills amplitude as a vector indexed by the cyclic ordering multiplied from the left to this matrix S defined on the previous transparencies, multiplied from the right with another vector with sigma tilde. For n equals 4, it's basically graphically the graviton amplitude is a product of the Yang-Mills amplitude divided by the B adjoint scalar amplitude, and basically if n is bigger than 4, then basically you should really read that as a matrix equation. So now let me come to positive geometries and canonical forms. So that was, okay, first I have to say basically about, if I think about differential forms, basically a multivariate case, so in more than one variable, and basically I would take out one variable and say, okay, when does it have a pole in this variable? It's basically, if I can write it in the following way, that basically I parameterize some hypersurface basically by the remaining variables, and basically if I write it basically as dz over z times something which lives on just on the space of the hypersurface plus some term which does not have a pole in z, then I call basically the residue of this form basically is just this psi restricted to this hypersurface with z equals 0. And I can do that iteratively, and that defines basically what a logarithmic singularity basically of such a differential form is. Now, canonical forms and positive geometries, they became popular in physics by this article by Nima Ahmed and collaborators, and they say basically, okay, let's define them recursively. Basically, if you're on a zero-dimensional variety, a canonical form is just a function, and this function should have the value plus or minus 1. Basically, canonical forms should only have singularities on the boundary of some space. The singularities should be logarithmic, and if you calculate the residue, basically it's a differential form of dimension 1 less. It should be again the canonical form of a lower dimensional space. So basically, these are basically the axioms for positive geometries and canonical forms. And this was basically a little bit motivation for us to look basically into the CHY formalism. How can it be basically married with this statement about canonical forms here? And okay, that basically, the third motivation comes from a paper by Sebastian Misera, who showed basically that the three amplitudes we discussed before can be written as twisted intersection numbers. So basically, we had these functions before. We can ask basically how do they transform under Möbius transformation. They transform with this weight, and then you can ask basically how does the measure transform, and then you find basically that this combination measure times these functions basically is invariant. So basically you can really view them basically as n-3 dimensional forms which are invariant under Möbius transformations. And then, okay, we've seen this definition of twisted intersection numbers already a few times. So if you basically have differential forms, you can assign to them basically a twisted intersection number defined by that thing here. And the twist is given basically by some connection. Okay, I used here the name eta. Previously it was always denoted by omega here. So the question is now basically, if we go to the CHY formalism, basically, what is our twist? What is our eta? What is our omega? And it's very simple. Basically, it's just basically this, the defining equations for the scattering equations times the differential in this respective variable. And then basically Sebastian Misera showed basically that these three amplitudes basically are just the twisted intersection numbers of basically forms which are either have the cyclic order as information or the polarization of as information. So now the question was for us basically, does this fit nicely with the idea of positive geometries and canonical forms? So that brings me basically to the last part, basically to the geometric interpretation of scattering amplitudes. And basically, so think about basically scattering amplitudes in these three series given as intersection number of two forms. One form encoding cyclic information, the other form encoding spin information. So basically we talk about two forms, one cyclic and one polarization. These forms basically are differential n-3 forms basically on the moduli space M0n, compactification of that thing. And basically the amplitudes are intersection numbers basically of these two forms. That was shown by Sebastian Misera. Then basically to have a nice theory, we would like to have that basically the only singularities where these forms become singular are basically on the divisor, basically compactification without basically the bulk. We would like to have that the singularities are logarithmic and basically the residues of the singularities factorize into scattering forms of lower points. So our contribution to this subject was to show that basically these points are rather simple for the first one, the cyclic one. Our contribution was to show that points 3 and 4 also hold for a suitable definition for the second differential forms, that you only have logarithmic singularities and they factorize. Okay, how does that work out? Basically, the first differential form is rather simple. You just take this Poincare factor or cyclic factor and basically just takes the measure n-3. So I recall that the Poincare factor basically was that thing here. And then you basically go through all the steps, verify everything, basically go basically from the z coordinate basically to cross ratios, verify you only have simple poles in these coordinates, and everything works out there. So this is basically more or less straightforward. The second part, you need also basically one which basically carries the information about the spins. Again, we write it basically as a function times basically a n-3 dimensional differential. And we cannot take basically the reduced Pfaffian for that. The reason is, if you work out what the reduced Pfaffian is, basically, and write it basically in the variable z, basically you discover basically double poles and higher poles in z. This is not what we want. Basically, we said basically explicitly, we really like to have basically differential forms which just have simple poles, just logarithmic singularities. So basically the reduced Pfaffian does not have that. It's not a problem for the reduced Pfaffian or for the CHY formalism, because in the end you just calculate basically the amplitude as a sum over residues on the solution of the scattering equations. The solutions of the scattering equations are a zero-dimensional subvariety in this moduli space. This moduli space is n-3 dimensional, so it's just, you need the values for physics, you only need the values on certain points. What we are asking here is much more. Basically, we would like on the complete moduli space to have a nice behavior there. So, how do we do that? And basically, we already know that basically these things here basically have the nice properties, just logarithmic singularities. So we can use them as a basis and dress them up basically with the correct thing that basically everything works out. So it turns out the way we have to dress up these things is basically just exactly the BCJ numerators for these multi-peripheral graphs. Okay, BCJ numerators we can calculate by other means. We can get them, and then basically we dress them up, and basically we do basically just need basically the cyclic factors where we fix two legs and then permute over n-2 factorial permutations of the remaining legs. So basically overall multi-peripheral or overall comp graphs basically. And then basically the sum of it basically gives the polarization function. Okay? Then of course you have to verify that if you use this definition here, first of all you get basically your physical amplitudes out of that. So you have to verify that on the solution of the scattering equations it agrees with the reduced Pfaffian. You can show that it does. You would also like to have some additional properties. For instance, this polarization factor should not depend on any cyclic ordering or on any singling out any particular particles. Here in the definition I treated particle 1 and n, basically the ends of the comp of this multi-peripheral graph, special. These are special, all the others are treated equal. And you have to show basically that this definition is really invariant under the full permutation group. Again, you can do that. You can show it's invariant under any permutation of your external particles you can think of. So this is a good definition. And then basically all the other properties, basically the logarithmic singularities are rather straightforward once you have shown that the cyclic factor has just logarithmic singularities. It does. And then you just have to verify that the residues are again basically exactly of this form just with lower points. Again, you can do that and it satisfies again C6. So basically in principle what that does, basically it tells you basically you can think about the three amplitudes given by two differential n-3 forms which live on the moduli space M0n, which have really nice properties. Basically the properties, they look a little bit mathematical, but I think they're really nice. And basically just basically these two scattering forms basically say they determine really the three theories. They're really linked together basically. So it's just two scattering forms determine three different theories. I think I put some information here in this talk just to wrap up basically how, for instance, you can calculate the graviton amplitude. So, of course, the first most dumb way to do it just to sum over all Feynman graphs. But this is a tremendous cost for 5, 6, or 7 gravitons, so nobody wants to do that. So the first efficient method basically is to use color kinematics duality. You first find out for Young-Mills theory your BCJ numerators, and then just square them, and sum over all trivalent graphs. We've seen basically the CHY representation, which boils down just to a global residue of these two functions here. We have the KLT relations. If you know the Young-Mills amplitude and basically the B adjoint scalar amplitudes, you take the inverse matrix, multiply them together, you also get the graviton amplitude, and basically the last point I was talking about, the intersection number basically of a differential n minus 3 form with itself. So that brings me already to the conclusions. So I really like this geometric picture, complete amplitude given basically by an intersection of n minus 3 forms. I really love that. But of course it basically raises some question. I mean, we just have two differential n minus 3 forms. They determine 3 theories. So the question is obvious, are these differential n minus 3 forms a little bit more fundamental than the 3 theories? You need, yeah. So, and of course basically makes manifest basically the amplitude and does not expand it in Feynman diagrams, so it sums up all Feynman diagrams at once. Caveat, of course, I was only talking about 3-level diagrams. Let me be clear about that. So it's not loop amplitudes here. So, but of course we would like to know, does this generalize to loop amplitudes? So let me finish basically. If you're interested in the various topics I mentioned here, I put up some references here. And thank you for your attention.
So yeah, that's time for questions. That's going to cost us to some. Okay. So by the way, can we go back on transparency too, where you have all this formula together? Okay, here. Okay, I may remember how to calculate this third line. If you talk about the amplitudes, I mean, of let's say Berenskill recursion or something like that. I'm wondering if you had some time, you or some student, to look at these 4 lines and see what are the performance, what are the numbers you get from that. If you can actually calculate, let's say, put momentum and polarization and calculate things. For instance, also if you can prove with some of them easier, let's say, this Parkin-Taylor formula or things like that.
Let me first ask a question. Back basically, are you asking about calculating the Young-Mills amplitude, or you're asking about, for instance, the gravity amplitude?
Young-Mills.
For Young-Mills amplitude, the fastest way is, as you mentioned, basically Berenskill recursion relations.
I mean, have you tried this intersection number? Is not.
Of course,
yes.
I calculated some of these amplitudes symbolically in a computer algebra system in all 4 ways. Yes, but if you really ask for speed, my advice is really off-shell Berenskill recursion relations for Young-Mills amplitudes.
And the second
for gravity,
yes,
I don't want to write down all the Feynman rules, no?
No, it's okay.
So I would basically maybe opt actually for the third line here.
Half question now. You talk about now this kind of theories. I mean, is there a kind of extension to other theories like fermions, massive particles, or whatever?
To some of the things, basically, yes, we actually also worked out basically what are basic BCJ relations basically for things with massive quarks, massless quarks. Yes, this can be worked out, and actually Leonardo.
More or less for the intersection, which is the last one.
For the intersection, we didn't do that. What you get basically, you have to redefine a new form basically, because if you want to have fermions, this have spin 1/2 basically, so you cannot put it basically, I mean, you need something new here. No? This is clear. We didn't do that.
So I have a more structural question for your gravitational scattering amplitude. So what are some type of the features that the individual terms in your intersection number representation of the gravitational scattering amplitude have? Like, does it have like spurious poles. For example, KLT, you know, in individual terms in KLT you have spurious poles. So I'm just trying to gauge of like, in comparison to that, what does this intersection number representation look like? If you write down something explicitly, for example, for like a 5 or 6 particle gravitational amplitude. So let's say NMHV amplitude split helicity.
To give you an answer, basically, how do you calculate the intersection number? You look up in the papers by Sebastian. Now, he says, basically, the best way to compute it, basically, if they only have logarithmic singularities, you get them from basically a global residue of the critical points. So if I would have to compute these intersection numbers, and since I have shown there exists a form which only have logarithmic singularities, I can use exactly this formula, and then it boils exactly down to the work of ZHANG and Matsubarara-HEO, who says, okay, I have to calculate a global residue. I can do that without knowing the roots, basically where the solutions of the basically scattering equations are. I just need basically an H basis or a Gröbner basis. So that's basically what is involved in computing the intersection numbers there.
But then you plot that into the BCJ numerators that you got.
The BCJ numerators are set independent. So I don't have to plug in anything there.
Maybe we can talk later.
Yeah, so may I ask about the status of the one-loop ZY formalism? So you say this is an intersection number computation. I suppose it's this intersection number on this Riemann sphere, isn't it?
Yes.
If can you do this kind of similar thing for the torus and try to get the one-loop ZY amplitude out?
I didn't work on that subject. I think Yvonne Geyer, Ricardo Montero, they have papers basically on the one-loop generalization of these formulas. Not the intersection number, but in the ZHY formalism. And then I think basically you can try basically further generalize what that would be in this intersection business. I believe this is probably possible.
So everything here is in d dimensions. You don't specify the helicities on the polarizations.
Yes.
Yes.
Yeah.
So, is there a difference in the way that you calculate things if you restrict to 4 dimensions, where you see extra simplicity in the amplitudes appearing? If you go through any of these approaches, right? So in the KLT, for example, if I fix the helicities, then I immediately see the compactification before I start constructing the gravity amplitudes. Do you see similar simplifications in the intersection number or these residue type calculations?
It's basically, you get the same simplifications everywhere. Basically, for instance, you would, instead of having basically, symbolic polarization vectors, you would use spino-helicity method for the polarization vectors, which give you basically, if they're dotted into the reference vector, chosen appropriately, they give simplifications. That occurs basically, I think, for everything here. It goes through.
There's nothing particularly special.
There's nothing. No. It's basically in this talk I really kept basically the polarization vectors. I never used basically spino-helicity for those, but you are of course, if you're interested in 4 dimensions, you're absolutely free to use them. And basically then you can choose a clever basis of polarization vectors to get all the simplifications you usually get.
So I don't see any more questions, or we can continue discussions over the coffee break, unless you had anything to add. The coffee break is in the same place we had this morning. So. Very good. So I think we're ready to start the last session of today. And Sergey Jeyong, hopefully I can get that close enough, is going to tell us about computing cohomology intersection numbers from GKZ geometric systems.
Thank you very much for the introduction, and I'd like to thank organizers for arranging everything. Thank you very much. And I am primarily interested in the theory of partial differential equations, especially from the viewpoint of algebraic analysis. But for several reasons, it's too loud. Is it okay? Recently, I became interested in this hypergeometric functions and its application to cohomology intersection theories, numbers. Sorry. And let me fix basic notations. So I call this type of integral GKG hypergeometric integral, which is actually a function that I will explain it. So here HL Lohan polynomials in x variables, where x is a coordinate of the algebraic n torus, it's a small n torus. And gamma, L, and C are supposed to be generic parameters. So, and here phi is just an algebraic n form whose poles are only along the branching locus of the integrand. And gamma is a cycle which is not specified in this talk, but when you want to prove something something essential, the explicit construction of cycle is very important, but I omit the detail today. And here the coefficients z are regarded as generic variables, so that the resulting integral is a function. And this is actually a solution of the so-called GKG hypergeometric system, which is a particular class of holonomic D-modules. But today I don't want to discuss such technical details, but I focus on the twisted Durham theory only. And the modern point of view to understand this type of integral is the language of twisted Durham cohomology groups, which has been discussed by many people in this conference. So D is the branching locus of the integrand, and XZ is the ambient space, which is defined as the complement of this divisor D in this algebraic n torus, and capital phi is the integrand. And with the aid of this integrand, we can define the twisted differential nabla in this way. And this is standard, and it is important that this is an integrable connection, so that you can consider the so-called algebraic Durham complex, which consists of algebraic differential forms with poles only along D and differentiation nabla phi. And the cohomology of this complex is called algebraic Durham cohomology group. And this is an algebraic object, but it is important that this is dual to something topological. So let me define the local system L dual to be the kernel of the analytification of this connection, whose sections is exactly determination of this multivariate function phi inverse. Okay. And the pairing defined by means of integration along twisted cycles is a perfect pairing. So this is called the twisted period pairing, where H sub n is the homology group with coefficients in this local system. And this is a consequence of compatibility of algebraic Durham cohomology group and analytic Durham cohomology group, known as the Rini-Grothendieck comparison theorem for regular singular connections. But an important point of view is that several properties of hypergeometric functions can be derived in a systematic way from this viewpoint, and this was first remarked in a systematic way by Amoto. And
Could you just say who G, K, and Z are?
yes, I was going to mention their names later on, but Gelfand,
Yes.
Kapranov, and Zerelinsky.
Thank you.
Okay. What? Ah. So today I'd like to focus on one aspect of this pairing called cohomology intersection theory, which is defined as the cup product and argumentation. Yeah. So this is a duality between cohomology groups and cohomology groups with compact support condition, which was discussed by a talk today. But today parameters, in this talk, parameters are supposed to be generic, but the polynomials are supposed to be general. Okay? And the starting point of our argument is this result by Cho and Matsumoto, which states that the quadratic relation of hypergeometric functions can be regarded as a consequence of the so-called twisted period relation, or just twisted version of Riemann-Hodge bilinear relation. And a typical example of such an identity is this one, where 2f1 is just a Gauss hypergeometric series. This is a classical example, and it is interesting in its own right. But the important point of view of Cho and Matsumoto is that the right-hand side is essentially the cohomology intersection number. So they developed a systematic method of deriving this type of functional identity. Okay, so this is my motivation. So I would like to explain what the twisted period relation is. But before going further, let me give a remark on the current state of research. So Cho and Matsumoto developed a systematic method of computing cohomology intersection numbers for a certain class of hypergeometric functions or integrals. And these hypergeometric functions both have one-dimensional integral representations, so that the computation of the cohomology intersection number is just based on residue calculus, which is very simple. And inspired by this result, many people try to extend or generalize this type of study to more general system of more general hypergeometric systems. And the most successful class is the so-called Grassmann hypergeometric system. And today, in this system, the polynomials, Logan polynomials, are all linear polynomials. So they are polynomials of degree 1. And the study of this system is related to the study of hyperplane arrangement, from which you can obtain a lot of combinatorial formulae. But today I'd like to discuss even more general setting. Therefore, it is not a straightforward generalization of these studies. So we need to develop a different method. Okay. So let me formulate a twisted period relation. This has been discussed by many people, but let me fix the notation at least. So I consider as many as 4 different homology and cohomology theories. This is the algebraic Ram cohomology group, and this is homology group, which is isomorphic to the cohomology group with compact support conditions through Poincare duality. And then it is natural to imagine that there is a dual homology theory, and this is it. So this is called the homology group with locally finite conditions, or known as Borel-Moore homology group. But the point is they are all equidimensional. So if we take bases of these theories, we can consider as many as 4 square matrices. P is the period matrix, PDL is the dual period matrix, and ICH is what we want to understand. This is the cohomology intersection matrix, and IH is the homology intersection matrix. Here H stands for the homology intersection, which is defined as the local intersection, geometric intersection of chains. But I don't need the precise definition of this pairing in this talk. I keep it implicit. But this plays an essential role actually. But it's only 40 minutes, so let me omit some details. So the twisted period relation states that these four matrices are not independent, but satisfy this type of compatibility condition. And the first purpose, the purpose of this talk is to extract as much information of the cohomology intersection matrix as possible from this relation. But there's a difficulty. So the first difficulty is this transcendental object, which was discussed by the person sitting in the middle. Sorry, I'm bad at remembering names, for general twist, it is not an easy task to find the basis in a nice way. But as for algebraic drum cohomology groups, there is a complete algorithm based on Grabner basis techniques, which was developed by Hibi, Nishiyama, and Takayama. So this is computable, and there is a very important condition called regularization condition, which relates this transcendental object to something algebraic. So this theorem states that the cohomology group with compact support conditions is canonically isomorphic to the algebraic drum cohomology group with dual twist when the parameters are generic. So here Gelfand, Kaprano, Serevitsky, same people. And this was established by these people. And non-resonance condition is just a genericity condition. But if you assume this condition, then we can assume that these psi i's are all rational differential forms, which is computable again by this algorithm. And I am sorry for this terminology. There are a lot of regular conditions in life, so the word being regular is too standard. And so the first information we can derive from this regularization condition is the differential equation for the transposed inverse of the cohomology intersection matrix. So let me first consider primary equations. So P and P duals are essentially hypergeometric functions because here entries are of this form, and these are essentially hypergeometric integrals. And they should satisfy a certain type of system of partial differential equations, which is called Gauss-Manning connection. Probably the most rigorous way of defining this is to employ the language of direct image of D modules, which is written in my paper on the archive. But please be relaxed and imagine just regard this as a standard system of partial differential equations. And then I look at the twisted period relation. I put I to be the transposed inverse of the cohomology intersection matrix. And what I do is something very simple. I just take the exterior derivative of this relation. Then the information on the left-hand side is completely killed. But from the right-hand side, what you get is three terms from the Leibniz formula. And this is what I call the secondary equation. This is again the system of partial differential equations for this capital I. And the first result of the talk is a characterization of the transposed inverse of the cohomology intersection matrix in terms of this differential equation. So I assume the regularization condition. And under the regularization condition, the secondary equation is regular, by which I mean this is Fuchsian. Not only that, any solution, any rational solution of the secondary equation is up to constant multiplication equal to the transposed inverse of the cohomology intersection matrix. And at this stage, the important point is that on the left-hand side you have no geometry. This is just about solving differential equation. Okay? So let me show you an example. So I consider this type of integral where capital phi is given by this formula, and this is a Lohan polynomial. But if you take out this y inverse, then this is essentially a quartic polynomial. And the interesting case is actually when the parameters are half, 1, 0, and variables are restricted, like this, z1, z2, d3, g5 are all equal to 1. It is because in this case it is the integral is related to the period matrix, period integral of a family of K3 surfaces discussed by Narumiya and Shiga. But this case is resonant and non-generic. But so it is not easy to apply our result directly to this case, but I would like to come back to this non-generic situation at the end of this talk. So for a moment, let me perturb the parameter in this way, and I take the restriction to this special subspace. This is not a restriction at all, because here you have 4 restrictions, but here you have only 3 restrictions. And you have freedom of scaling x variables and y variables, which kill 2 variables, 2 independent variables. And you also have freedom of taking off 1 coefficient from this factor. Then you take it out of the integral. Then you can reduce the number of variables from 5 to 2. This is called a torus reduction. Then, by applying our method, you get a basis of the twisted Durham cohomology groups. This is the basis for the algebraic Durham cohomology group and the dual Durham cohomology group at the same time. Okay. Thank you.
What is epsilon here?
Epsilon is a small parameter.
What?
Small parameter.
To avoid resonance?
Yes, for non-resonance. Okay. Then I can solve the secondary equation, and this is one solution, one non-zero solution, and where Cij is rational functions of this form.
Can I ask you a question?
Yes.
The difference between the two cases, epsilon equals 0 and epsilon different to 0, the dimension of the cohomology class is the same?
The dimension. No, I don't think so. It decreases.
And why then you keep 4?
Because I need to apply our general theory to this case. Then I want to take a limit to obtain the result for the case when epsilon is 0. but at this moment it is not non-zero. Okay, so you are lucky in this example, because usually the computation of Grobner basis takes a lot of time. But it is better than nothing, and it is important that there is at least one algorithm for general case. But it's not the end of the story, because it determines the transposed inverse of the cohomology intersection matrix up to constant multiplication. So we need to determine this constant. For this purpose, I need to extract more information from the twisted period relation. This ambiguity actually comes from the obvious reason. Yeah, I took the derivative. So it kills constant. This is why. And so I rewrite the twisted period relation in this form. And this separates the role of the both sides of the equation. The left-hand side is what we want to understand, but the right-hand side is what we should understand. And P and P dual are both solutions of a certain holonomic system called GKG system, which enjoys very interesting combinatorial structures, such as the combinatorics of the secondary fan or secondary polytope, which is a very important subject in mathematics. But unfortunately, if I go into details, I might run out of time. So let me explain the general picture of the combinatorics of the cohomology intersection matrix derived from this combinatorics. So in order to explain it, I need to prepare several terminologies, but they are all elementary, and this is they are Newton polytope and normal fan and Rohan expansions. So a priori, the cohomology intersection matrix is a rational matrix, so you can take off the common denominator, small f, and what you consider is the convex hull of the exponents, alpha, with non-vanishing coefficients. And this is called the Newton polytope, which has been known more than 300 years. And then what you do is to extract the combinatorial information from this convex body. Namely, to each facet you associate the inner normal vector, from which you draw a ray. And if you repeat this process, you get a subdivision of the vector space into convex polyhedral cones with nice intersection properties, which is called a fan in mathematics. Okay. And why do I consider this type of object? It is because from this combinatorial object we can construct a geometric object which helps me to understand the local behavior of the cohomology intersection matrix. So from this, once a fan is given, it is there is a standard machinery of toric geometry from which you can construct toric compactification of the torus. So unfortunately, this is a bit technical, but normal fans may contain cones which are not properly convex, so it is only partial compactification, but this is about technicalities. So there is a variety which contains the torus, so this is the point. Okay? And then what you do is to understand the local behavior of this fraction 1 over f in terms of the geometry of this variety. So what you do is very simple. You pick up one vertex. We say alpha 0 is here. You pick up a vertex, maybe. No, it's okay. So you pick up a vertex. then it corresponds to exactly one cone here by construction. Okay? This has the information of facets, and therefore the information of rays, which corresponds to a cone. And if you are given a cone, it corresponds to a very special point of this geometric object. So let me call it Z0. Then this corresponds to the origin of the radius of the domain of convergence. So you take out the leading term of this polynomial f, and here is the rest of it. And what you do is to plug in the expansion formula of Neumann series. So it is, please do not switch the camera. So you plug in this one into this formula to obtain a Loran expansion, which is convergent around this torus fixed point. So this is a picture. And in this way, we can understand where we actually are. Okay. And the second theorem, which is more complicated, is the following. So the secondary fund, this is a mathematical structure. This is also a fund, so subdivision of the vector space into convex polyhedral cones. This is a refinement of the normal fund. So please notice that we don't know what f is at this stage. Okay? But actually, this is a refinement. And moreover, at each torus fixed point of the toric variety associated to this secondary fund, there is an explicit formula of Loran expansion of the cohomology intersection matrix around this special point. Okay, there is a formula. I will show it to you by means of an example. Time permitting, I'd like to show you the general version. Okay, so here the secondary fund is something computable. In the worst case, partially. I mean, by which I mean you can at least compute several cones of this combinatorial object from the information of the integral. Okay? So if you look at the integral, okay, you have the information of exponents, and you can actually compute this combinatorial object. But then at each torus fixed point, you can understand the cohomology intersection matrix. So let me show you an example. This is not easy to describe in a general fashion. So let me remember what we computed. So this is the integral. Okay? And this is the part of the parameter, this is the specialization, and this is the solution of the secondary equation. And this is up to constant multiplication equal to the cohomology intersection matrix. But we want to specify this, we want to detect this alpha. So by brute force computation, you can show that the transposed inverse, one entry of the transposed inverse of I is equal to this quantity. So if you take a look at the 1-1 entry of this equation, then it is reduced to this equation. So if you can understand this guy, then you are done. So the secondary fund in this example is given by this picture. For technical reasons, I equip the axis with these coordinates, but this is standard in toric geometry. And let me take a close look at this cone. So please remember that. Please do not switch the camera. So you have this geometric object, then each cone corresponds to a special point. And actually, if you draw the dual diagram, you can show that, you can imagine that this is the picture of the toric variety. Here you have special points, they are connected by special orbit, and here you have the entire space. And I take a look at this special point here, whose neighborhood is explicitly given by this inequality. So this is nothing abstract. This is automatically computed. This is very easy to understand. Explicit. Okay? Then the general expansion formula of the cohomology intersection number in this case takes this form, where I take the restriction to this special, very special subspace, but the general formula is valid. I mean, there's a general formula for various z's, okay? Where phi I and phi I dual are hypergeometric series of this form. So this is phi 1. This is the, you see that the coefficients are just ratios of gamma functions. And here you have a ramification factor which cancels out each other. So you don't need to worry about the multivariateness of this term. Okay? And here, and you also have the same similar series here for phi 2, and phi 3 is similar. But so in any case, I have an explicit expansion of the cohomology intersection number at this point, okay? Near this point. Then what I do is something very, very easy. So these are series in Z4 to the -1 power. These are all series Z4 to the -1 power, which is compatible with this convergence region. So I substitute Z4 equal to infinity to obtain this constant. But a priori, this is a constant because here I have already solved the secondary equation, and this person is constant. This does not contain any z variables. So this should be an identity. This should be true for any variables. Okay? And from this formula, you can determine the constant multiplication, alpha, in this way. Okay, let me take a limit of this. Let me finally show you the limiting case. So I want to take I have determined the explicit formula of this cohomology intersection matrix now. It is just this one. Okay. So I just substitute this formula to the previous formula and take the limit in a nice way. So if you just take the limit, it diverges, because here you have here it does not produce any problem, but here you have some problems. So what I do is something standard in the theory of differential equation called the Frobenius method. If you have when you take the limit, several ramification factor coincide. So you take the difference and divide it by epsilon to get well-defined limits. So here is the result. But let me take a closer look at the components here, phi tilde and phi tilde dual. This corresponds to an interesting identity of hypergeometric functions. I will show you. So phi tilde 1 is just given by hypergeometric series. This is actually a hypergeometric series, and with ramification factor here. And phi tilde 2 and phi tilde 3 contains a logarithmic term. And phi tilde 4 has log squared. So this is even more strange, but this means that the local monodromy is not diagonalizable at infinity. And if you expand these coefficients, you get more messy formula. So here you have some big rational number, Euler-Mussolini constant, and special value of digamma function, and so on. So as for phi prime to 0, it's complicated, but as for phi prime to 1, it's much simpler. And the next term is much more complicated. You have very big natural numbers and Euler constant, digamma, over some big natural number. This is only the constant term. And the next term is also a mess. But the point is they fit into this simple identity. And we have similar formula for phi tilde 1 and phi tilde 2, 3, phi tilde 4. So here, so as I said, the rank of the cohomology group reduces from 4 to 3, but this is explained by this equality. Well, actually, when I take the limit, I forget about this framework of cohomology intersection theory. This is just an identity of functions. Okay? And you can show that the first entry is nothing but the ramification factor times Thomae's hypergeometric series, which is nothing but a square of Gauss to F1. This identity is known as Clausen's identity in mathematics, which is very, very classical. But I am not sure if this type of explicit identity is known in the classical context, but because this identity involves a lot of logarithmic terms. But this is one application of our method. And I only have 3 minutes or something. I've already run out of time. 5? 5 minutes. So maybe I can show you the general formula of a general expansion formula of the cohomology intersection numbers into series, but I don't think I am able to explain the details. Let me just show you the formula. Okay? So formula is just here. Okay, so there are a lot of technicalities, but this is the cohomology intersection number that we want to compute. So you need to choose a special form of this form, but if it's a log form, it takes this form, a linear combination of this form. And this is expanded into a certain series, okay, where phi is a hypergeometric series in several variables. And here you have sign factors, but this is an exact formula convergent at the torus fixed point. So this T corresponds to the torus fixed point. Okay? So I explained the meaning of this formula briefly. Then that's the end of my talk. I think you can switch the camera. So let me explain at least what is going on. So you have integral. And from this information, so you have combinatorial information of the integral, by which I mean the combinatorial information of exponents, from which you can construct a combinatorial object called secondary fun. So I don't know what kind of fun I get. So this is the secondary fun. secondary one, which corresponds to a geometric object called toric variety. And if you pick up one torus fixed point, this is very important. There is a theory of Gelfand-Kaprano-Zelebinsky, which interprets this point, this special point, into a special subdivision of a particular convex polytope. So this is a great discovery of 20th century, but this is a triangulation of a polytope which consists of purely combinatorial information, from which we can get a general formula, general expansion formula of the cohomology intersection matrix number. So this is expanded into series. Thank you. So here you have the explicit form of the hypergeometric series, which appear in the general expansion formula. But this also involves a lot of information of combinatorics of the triangulation. But there is an algorithm or explicit formula to compute this type of series. So this is an exact formula, and you can make use of this type of formula to obtain interesting functional identities of classical analysis. No, I skipped this. So thank you very much for your attention.
Right, so thank you very much for this talk. Any questions or comments?
So when you take when you want to determine the constant, the alpha constant, so you have to take the limits on the series of the canonical series that you get, right?
Yes, here.
This series, yeah. So you say that this limit on the series is, I mean, it's always can be taken. Can this limit always be taken?
Yeah, in some cases it diverges, but then you can just multiply the divergence factor to this cohomology intersection number so that it converges. You see what I mean? If in some cases you have 1 over z4, for example, here, but then what you do is just to multiply z4 to the both to this equation and take limit. Then it should converge because this term converges.
Right.
So it's always possible.
Okay, this is not really a question, it's just from my curiosity. Are you aware that, because somehow you are looking for some boundary terms here with this equation when you differentiate?
What do you mean by the boundary term?
This constant, you say. You try to find the constant, okay?
Yes.
Are you aware that in Feynman integral calculus we're also doing this by looking for asymptotic expansion of Feynman integrals and basically using exactly this polytope stuff to do these kinds of things? Are you aware?
Yeah.
Are you aware of that, or?
No, I have never worked with this, but I know what you mean. Yeah.
Could you show again so you mentioned that in this as epsilon goes to 0, you lose one of your bases of function.
Yeah.
So the dimension is the space is smaller.
Yeah.
So what happens is there I see. So phi 2 and phi 3 become
the same.
And if I take phi 2 minus phi 3 and you divide by epsilon, do I get some interesting new function?
Phi 2 minus phi 3, but I have already taken the limit in this example. What do you mean? Sorry. Okay. From the beginning, actually, phi 2 and so here you only have two functions, but it is you have two here. So this actually means the following thing. So if you so the algebraic parameter, the dimension of the Durand cohomology group is 4. So therefore, this should be equal to the dimension of the solution space of the hypergeometric equation. Hypergeometric equation. But so you take 4 solutions. I should write it. 4, 2, 5, 3. They are all independent. You should have 4 independent solutions. But if you take this special restriction, these two terms coincide. Yes. So I know what the limit is. Therefore, I take this type of limit, and then only after that I was able to obtain an interesting functional identity.
Okay, thanks.
Thank you.
Okay, yes. 14 minutes. Okay. Yes, yes.
Very good. So we'll start the last talk for today, and Yang will tell us about modular intersections as a powerful method for identity.
Okay. Okay. So first, I thank the organizer for organizing this very wonderful workshop. So I think I learned a lot of things in mathematics and also physics. So today I'm going to talk about this module intersection method for the IBP reduction. So first I have to apologize that, maybe this is the last talk today. So this talk is a little bit on this kind of traditional side. So I still have this kind of linear relations between the Feynman integrals, okay. But I try to use the so-called module intersection method to get simpler relations and then to make this kind of Gaussian elimination easier or sometimes from impossible to possible. Okay. Oh, another thing I need to apologize. Okay, that's not the first thing, the second thing. So I used this word intersection for my method called a modular intersection. But I have to say that it's slightly mathematically slightly different from the intersection theory. Okay, we discussed a lot, which is a central topic of this workshop. So my modular intersection actually conceptually is very, very simple. So first recall that if you have this kind of linear algebra problem, okay, if you have a large space, you have several this kind of linear subspace, you try to find the intersection. We know, okay, if you know this kind of matrix language, if you have this kind of generating basis, if you can do some kind of Gaussian elimination, this one is a completely trivial question, okay. So here we say that we have this kind of IBP, okay, this is a vector space. We have a lot of IBPs. I try to put a different kind of constraint on that kind of space, okay. So it's very, very similar to this kind of linear subspace intersection problem, but I call it a modular intersection because the thing is here I have to consider all these kind of generators or this kind of constraints as polynomial vectors. So it's higher than this kind of linear algebra. Basically, it's a nonlinear algebra or from my companion talk by Janko Böhm. This is a computational algebraic geometry problem. Yes, as I said, this module intersection is to apply this kind of intersection of different kind of mathematically called polynomial modules. Basically, try to find some good IBPs, satisfy all these kind of constraints you want to put on this kind of IBP system. Then possibly you can get a new IBP system which is much smaller than kind of traditional system. Then maybe it's possible to solve it. Okay, so this talk, okay, is basically is a review of what I did in past several years, okay, with my collaborators from different cities in Europe, okay, from Uppsala, from Mainz, from Kaiserslautern, from Southampton. Okay, so first we developed this kind of conceptual things. What is this kind of module intersection? And gradually, okay, with the help of mathematicians, we find a way to really implement it and really try to use this one to solve some real life problems. Okay, so I don't want to say something more about this kind of IBP things. This is basically this is the biggest problem, okay, for our workshop. I just say that, okay, this one is a really fascinating problem because almost for all this kind of computation of Feynman integrals or amplitudes or some other things like this kind of study of transcendental functions, we have to use IBP. And in many cases, this step is really the most time-consuming and also the memory-consuming step for the computation. So this talk, the idea is very simple, okay. So suppose you don't have this kind of new ideas, you have this kind of very nice intersection theory, you can really project your input integral to this kind of mass integral space, okay. Suppose you still try to find the linear relations between the Feynman integrals as IBP relations, you try to do the Gaussian elimination. So from the computer algebra, we know that this kind of Gaussian elimination seems that it's a quite a harmless step. Okay, why? Because if you are working with a matrix, if you try to do this kind of Gaussian elimination with float numbers, okay, it can be done in polynomial time. Actually, suppose the size of the matrix is m, it can be done in the m cubic time. But our matrix is slightly more complicated than this. Okay, if you have an integer matrix, okay, in this case you can apply something called the Bayes algorithm. And if you do this kind of advanced version of Gaussian elimination, it's still polynomial running time, but the power will be increased from 3 to 5, so it's getting worse. But in this kind of Feynman integral, this kind of IBP reduction, so you know that there's a space-time dimension D, which must be symbolic. You also have the Mendelssohn variables. You also have this kind of mass. So I'm not quite sure if there's a proof this must be done in polynomial time. Let's say possibly cannot be done in the polynomial time. Okay, so if you have this kind of symbolic variables in this matrix, the Gaussian elimination is really hard. Then the idea is no matter how difficult this kind of Gaussian elimination is, you really try to truncate this kind of linear system. You make this matrix as shorter as possible. Okay, then you get a great speed up of the computation. Okay, so this kind of ideas is a very nice ideas from 2010, and first by David Cosworth and his collaborators. The thing is, in most of the cases, if you really consider this kind of amplitude from Feynman rules from unitarity, then most input integrals are integrals without a double propagator. Then you can choose a mass integral basis without a double propagator. Then maybe you can make this kind of shortcut. Okay. So in general, if you do this kind of traditional IBP, you will find that you have to go through a lot of integrals with double propagator in order to reduce no double propagator integral to this kind of no double propagator masters. So their idea is to apply this kind of algebraic geometry concept called syzygy to find some good vector directions to the IBP. Then you get a much smaller linear system. Then possibly you can really do this Gaussian elimination. So in I think in the duality there's a way, okay, by Roman Lee, this idea that is to consider this kind of integrals, which is always a scalar integral, which means this numerator is always 1, but you could have high power of the propagator. So if you apply this kind of Lie-Pomeranski representation and then you do this kind of syzygy story in this representation, then it's possible that you can just work with this kind of scalar integral with various power. So I have to say that these are very brilliant ideas. But if you really directly start with this kind of syzygy approach, okay, especially have multi-scales, multi-loops, that's very complicated. Then maybe even before you get this kind of truncated linear system, okay, already this kind of syzygy computation takes an infinite amount of time, or maybe you get this kind of memory leak that does not finish. So we need some way to really make it work. Yeah. So here I present this our group's module intersection method. Again, we list this kind of constraints of this kind of IBP relation, and then I translate this kind of constraint to the polynomial modules. And eventually, suppose I have several constraints, I just take the intersection of this kind of modules, which is similar to intersection of the linear subspace. Then I can find the good vectors, and then I do this kind of IBP. In this way, okay, in many cases, it's much, much faster than this standard, this kind of syzygy approach. So I have to say that in parallel of this kind of IBP, okay, this kind of module intersection IBP development, okay, I also need to mention, okay, there's a very famous method right now, okay, developed in Freiburg by Professor Harald Ita and his collaborators, is so-called numeric unitarity. That thing is you try to get this kind of good IBPs, maybe IBPs without double propagator. So instead of using this kind of IBP relation, okay, Gaussian relation, really try to reduce this kind of amplitude into the mass integrals. You insert this kind of good IBPs to your integrand, and then try to fit this kind of coefficients from numeric unitarity. So a lot of highly non-trivial new results are computed with this new method. Okay, so I think this one is very practical. Okay, so again, so I'm going to talk about this kind of IBP in the back of representation. So the reason I like this one is, for me, basically this kind of unitarity cut language is very good. So instead of considering this kind of IBP from top to bottom, I always try to apply some kind of spanning cut. Then I get maybe smaller linear system and it's easier to control it. Okay. So, but I don't think this step is really necessary. Okay, if the system is not big, then actually you can just use this kind of thing without a cut to finish all this kind of computation. So, okay, so let's review this back of thing a little bit. So start with this kind of standard Feynman integral in the loop momentum space. And then we convert it to this kind of back of languages. F is a back of polynomial, which is the determinant of this symmetric gram matrix. So here I dropped some kind of gamma factors, and also I dropped some of the constant gram determinant because they are related to differential equation, but not related to this kind of IBP problem. So in general, we could have this kind of IBP in the back of representation. So this AI itself, okay, that's arbitrary, but must be a polynomial, okay. If this AI, this you can think that since you have different indices, you can think that all this kind of AI form a vector, but it's not an arbitrary vector, okay, it's a polynomial vector. This AI must be polynomial. If you have some complicated pole here, then it destroyed this kind of back representation. So that's a polynomial vector. Okay, so if you take this kind of derivative, then you get 0 because we know that for this kind of Baikov representation, there's no boundary contribution to the IBP. And of course, okay, as we see from many talks in this workshop, we can feel free to set the sum of this kind of this to 0 and to simplify this problem to get a partial result. Okay, let's put some constraint on this kind of ace. So first of all, this one is very simple. Okay, if you look at this kind of expression, if you take this kind of derivative on f, then you can see the shift of the exponent of f, which means you get a mixture with this kind of dimension shift identity. So possibly you don't like it, then I put this kind of constraint, okay? You want this kind of AI dot product with this kind of partial derivative, which is again proportional to f. So this A is something you want to solve for, but this beta is also something you want to solve for, and all of them are just polynomials in Z. If you have this condition, then of course, okay, this derivative changes the power by 1, but this proportional coefficient just compensate this shift in the dimension. And then you can put some kind of constraint to say, if you don't want the increase of this kind of propagate power, then you can say you can put the corresponding AI proportional to Zi. So there's no increase of the power. Okay, I don't say it's no double propagate. So here I'm working with arbitrary integral. Okay, if you have this kind of condition and you start with some integral without double propagator, then always you don't have double propagator. If you have something with this propagator highest power 2, and you put this kind of constraint, you always have the highest power 2. You will never have 3. So I say it's no increase. I don't say it's no double propagator. So I have to emphasize again that all this kind of A's, they must be polynomials, otherwise they destroy this kind of Bicol representation. So this is to do this kind of IBP in the Bicol space with some kind of constraint. Okay, suppose I say I don't have a mixture with this kind of dimension shift. I don't have the increase of some power of the propagator. And then we can say that both of the two constraints is M1, M2. Okay, there are the solution will be some kind of polynomial module. Okay, then of course there are some kind of linear subspace. But I have to emphasize, since I work with this kind of polynomial component, so I call it a fancy name, polynomial module. But you know, it's just a linear space. I want to find the intersection of these two space. Then I solved all these kind of constraints. You can see both this M1, M2, they are pretty simple. Okay, especially with M2, you can find that you ask this AI proportional to Zi. Then of course this kind of all generators are already found. Okay, so which is this kind of Zi cofactor times a unit of vector. So this completely solved. So this one looks a little bit difficult, but as you know, it's completely trivial. So we put this kind of constraint on our A, this kind of factor of the derivatives. Okay, we ask that the dot product between these partial derivatives with AI is proportional to f. Okay, so you can see the syzygy equation for this kind of Jacobi idea. Okay, that's a fancy name. But the thing is actually, okay, you may think that, okay, think this is a standard syzygy problem, you have to run this kind of Schreier algorithm, go through the global basis computation, do everything and try to get the syzygies. Of course it works, but it will get a very messy result and it's very slow. Okay, so we don't use this way. So here we apply this Roman list trick from 2000, I think 2013 sometime. So you can see we are solving this kind of syzygy equation for their components. But you know this f is a very special polynomial. It's a determinant of symmetrical matrix. And if you have a generic matrix and all the components are just free variables, and then you can have that relation. So what's the meaning of this relation? If you take this derivative of the determinant, then you will get this kind of determinant of the minor matrix. Then multiplied by this cofactor, you see, you get this kind of Laplace expansion. So clearly it's a syzygy. So with some known result from mathematics, we can see that actually this kind of relation gets all this kind of solution for that equation. I have to mention that there's a more fancy way to do this. Okay, so actually I extract some ingredients from Eric Panzer's paper a while ago. So the thing is, so instead of considering this kind of first order operator acting on f equals 0, you can consider this kind of polynomial annihilate of fs in the Weil algebra. then actually you could get this kind of first order differential operator or second order or higher order, this kind of things. And all of them will give you IBPs. So what I did here, okay, you can say just the first order. And it's easy to say that if you use this kind of simple relation, that just means you transplant this kind of canonical IBP in the momentum space to Baikov space. Nothing more, nothing less. Okay, but if you use this way, this more advanced way, I'm not quite sure, then possibly you get something, this kind of new relations, which is not clearly from this Feynman momentum integration. Okay, but here I just use the simplest one. I say I use this kind of first order relation from Laplace expansion. Basically means I just use all this kind of canonical IBPs for momentum representation. Okay, nothing more. Okay, sorry for the handwriting. Okay, I always have some trouble in writing this kind of big matrix with LaTeX. Okay, so suppose that you know this generator for both M1 and M2. Okay, then okay, of course it's a polynomial modular intersection, but it's just some very, very similar to this linear subspace intersection problem. So for M1, we know that there are some generators. So each one, this V1, V2, okay, that's a t-dimensional row vector. Okay, the t is just a dimension. No meaning. And M2 is similar, okay, it also has some generators. Then the question is, how do you find this kind of intersection of the two space? So if you really do this kind of thing over linear algebra, don't care about whether this kind of V and U, they are polynomial components, and also for the intersection, do you get a polynomial or do you get fractions? Okay, if you don't care about this, that's just a simply linear algebra problem. You write down this kind of V and this kind of you just do some Gaussian elimination, you immediately get it. But for us, we have to do something more because we want this kind of intersection generators to be this kind of pole-free. They must be polynomials. So we do something like this. This is the one of the non-standard way to get the intersection. So here what we did is we try to extend all this kind of vectors. So each one is a row vector. We try to extend it by this diagonal identity matrix. So for this huge matrix, we try to calculate the group basis, okay, with respect to the rows. So we are doing the group basis over this module space defined by the rows. And then we consider this ordering when the position is more important than this kind of terms. And then we try to say, can we find some kind of a group basis generator, okay, when all this kind of physical component are cancelled out to get 0. Okay, so in principle, you will find all such kind of vectors. So what's the meaning of that? If you find that you have some combination when all this kind of vectors, this original components are 0, that just means, okay, you find the syzygy relation between the generators, which means if you multiply by the cofactors, then you will get this common element in the two modules. Okay, so that's an efficient way to get the intersection. This kind of one here, okay, that's nothing. Let's just try to record what kind of factor you multiplied by this kind of vectors. Since this kind of V1 and U1, they are all, of course, they are polynomial component vectors, but they are at most linear, so this kind of group basis computation can, in general, can be done very, very quickly. Okay, so this is example. It's a very simple example. This massless double box. So this is a two-loop example. So I write down this kind of M1. So M1, this each row, okay, this is my generator for the IBP because I already solved this kind of Laplace relation. So I say I must do this kind of direction for my IBP reduction. It's very simple, at the most linear. This M2 here, I put somewhere this Z1 just means I don't want the increase of the index of the first propagator. But for the last, I just say arbitrary, I put everything there. And then I can talk about, okay, so we have this kind of two modules, you can take the intersection. Okay, again, it's very similar to this kind of linear algebra problem. But here, I want to take the intersection. I make sure that I get polynomial generators. So this one can be easily done by the group-based computation in singular, the new version of the singular is very, very fast. Seconds you finished, and everything is analytic. Okay, but for research problem, okay, if you just do this, still that's not enough. Then we can somehow use this kind of practical ideas. First, you can apply this kind of unitarity cuts. If you have unitarity cuts on that, you have few variables. It's much easier to do this kind of IBP truncation things. Second thing is actually when you calculate this kind of module intersection, so rigorously you really get all the generators by this group-based computation. But we find that for our physical purpose, we don't need all the generators. We just need the lower degree ones. Then it's much, much easier. We can set a degree bound and do this kind of computation. The last one is a generic trick for any kind of symbolic computation. So the thing is, if you have some parameters, minus some variables, or this kind of math variables, and you also have other variables, like this kind of Bickel variables or Feynman variables. The thing is, you may think that you want to feel free, okay, to divide by s, divide by t, or divide by s plus t, okay, since they are just constants for this kind of integration. But if you do this, it's definitely slow, because for computer algebra, actually, if you have this kind of fractions, you try to clean up it, it's very, very slow. So the trick actually is from the computer algebra, actually is from something like the primary decomposition. So the idea is you treat all these kind of parameters equally as your physical variables. And then you put a monomial ordering, you say the physical variable is higher than the parameters. You do the computation. Then there's no fraction at all. Then you can finish a lot of computations. It's called the localization trick. Okay, so with this kind of tricks, it's quite fast. So this one is a quite a long trivial example. So you have this kind of 5 minus some variables, and it's quite a long planar diagram. If you put a triple cut on it, and you calculate the module intersection, still with seconds you get all this kind of generators. So actually it takes no time. Okay, so after this kind of module story, then if you really want to do this kind of IBP okay, in the traditional language with some new ideas, you can say I put all this kind of spanning cuts. So I have different branches of the computation. For each one, I calculate this kind of module intersection. I truncate the IBP system. And then I can try to do some kind of Gaussian elimination, either numerically or do it analytically. So if we finished all these kind of spanning cuts, we merge everything together to get the IBP, okay, the complete one. Okay, this is a completely trivial example. So if you do this kind of spanning cut on double box, and of course you can say you have to determine what is the lowest mass integrals, which means if you collapse one more propagator, you don't get anything. Okay, so if you do this kind of step on each kind of lowest mass integral, you can do either this kind of triple cut or fourfold cut. And then you can run this kind of module intersection. You can get a very simple, very short IBP relations, and you can do this kind of Gaussian elimination on everyone. So again, so we see this kind of thing many, many times, like from this morning's talk, you can say if you do cuts on the IBPs, then you are somehow repeating this kind of mass integrals for many masters. For example, this one is the top sector. Then you have this kind of say D box 1, D box 2, but these two numbers will appear again in a different cut. So of course, you can use this one as a consistency check condition, okay? But we find that, okay, this example is completely trivial. For more complicated examples, no matter how you do this kind of IBP by cut, you'd better get rid of this kind of redundancy. So how do you get rid of this kind of redundancy? It's very, very simple. So we use this paper, this Cambridge paper about do this kind of row reduction. Okay, you can definitely set some of the mass integrals to 0. Okay, because when you do this kind of Gaussian elimination, this kind of mass integral actually this is a non-pivot column. If you just delete this kind of column, okay, beforehand and then do the Gaussian elimination, of course you have one column less. But then for all the other columns, suppose they are not a pivot, you still get the same numbers. So feel free to set one mass integral to 0 or several mass integrals to 0. So we find that for research problems, if you have this kind of overlap, this one mass integrals appearing in the two different cuts, just pick up one cut and set this integral to 0. It will speed things a lot. Also, I have to emphasize that I'm not talking about just this kind of low double propagator integrals. If you have something like from differential equation, you have this kind of double propagator integrals, I can also use this way to truncate the IBP system. So if this is a one loop example, that's a box example. So if you have this 2 here in the beginning, I already solved the model intersection for this ace. Okay, so in this case, if you're still trying to expand it with this kind of ace, but remember the factor 2, you will get some typical IBP like this. So the meaning of it is very, very simple. It just means I put a constraint on this number 2. I will never get something like 3. Okay, I will also never get something like 2, 0, 1, 2. Okay, so again, it's a truncated system a lot. Okay, that's for long trivial example. So suppose that you really want to do this kind of IBP analytically. I have to say it's a very heavy computation. Okay, so I will refer to my collaborator Yanko Böhm's talk this morning. Okay, so it's really a heavy computation, even with this kind of truncated IBP system. So with Yanko and his student, we rewrite most of our code, both this kind of module intersection part and also this row reduction part completely in singular. And suppose that if you really try to get this kind of analytic IBP reduction, then we suggest that you use a numerical fitting method and you try to make it as a massive parallelization program. So Yanko talked about that if you really try to do this kind of numerical fitting, then we use this kind of GPI space powered by the idea of Petri net. Okay, so look at this example. Okay, this is a long planar diagram. This 5 Mandelstam variables. So we know that from last year, okay, with the efforts of these 2 groups, you can see that the analytic results are all calculated. The next thing, of course, is you know this kind of analytical result for the master integrals. You still want to say, how do I reduce this kind of real-time long master integrals into this kind of UT master integrals? So that's an IBP problem. Okay, so with my collaborators, we tried this rank 4. Okay, of course, it's a test. I don't say that rank 4 is everything. Okay. We tested this kind of rank 4, but rank 4 is already quite complicated. If you try to use it with other commercial program, it's very, very difficult. It seems to not finished yet. But with our, this kind of module intersection method, we put this kind of triple cut and 4-fold cuts. Okay, and for each one, you can see that the number of the relation is just of the order of 1,000. And the number of the integrals is also out of 1,000. And it's a very sparse matrix with this kind of analytical coefficients. It's just like 1 megabyte. If you say, I want the physical one, we want the rank 5 numerator, we are still working on this, then you can see there's an increase by a factor of 3, so it's 3,000 times 3,000 something. But still, it's a very sparse, small matrix. I would say that actually we don't need the analytic IBP reduction. Okay, so the thing is you want this kind of IBP generated from this kind of integrand. But the thing is, as long as you have a small system like this, it's already quite truncated. So you have a small system like this, then just to do this kind of numerical reduction, like over finite field, that takes no time, less than 1 second, you get all this kind of reduction done. So if you can do all these kind of numerical things very, very fast, then you just try to accumulate enough numerical points, and then you directly fit the amplitude. You don't want to fit this kind of IBP. So I don't think this kind of analytic IBP is necessary. Okay, I just try to advertise, since it's already quite a small IBP system, if you do it in an ordinary way, you don't put any kind of constraint on IBP, so easily you can get tens of thousands or sometimes 500,000 relations like this. But this one is a small system. If you try to do it over finite field to do reduction, it takes completely no time. That's 1 second. Okay, but sometimes you say, if you really want the analytic IBP reduction, okay, we also spend some time on this. This kind of thing, they looks like quite a small matrix, quite sparse, okay, but if you remember, there are 6 variables inside that, 5 -1 variables and 1 space-time dimension. If you really try to do it, so we did that with this kind of fitting method. So Yang already talked about that for the hardest cut. We use this program. We wrote the row reduction program ourselves, and we run it with this GPI space for parallelization. So we did it with a semi-numerical way. We put some of the -1 variables to numbers, some are symbolic, and we have to run this one maybe 700 times. The total running time is like 12 hours. We finish the hardest cut. So for all the other cuts, the running time is shorter than this. Still, like if you have a cluster, okay, if you use this kind of things, if you really want this kind of analytic IPP reduction, you can do it in 1 week. It's no problem.
Sorry, Yang. Remember which sub-diagram this cut corresponds to?
It's a sunset diagram, but I don't remember which sunset. Yeah. But I also have to say that if you try to play with the numerical sector, it's much more systematic. If you try to play with analytic, then everything is tricky. When I say this one is the hardest, it just means on my program the reduction time is longest. Okay, but it seems that of course, if you want to everything analytic, you can use a lot of tricks, because maybe this just because this kind of -1 variable choice is bad for this kind of cut. So quite frequently, okay, for this kind of hard cut, then you can somehow change the definition of -1 variables, do a linear transformation, then suddenly speed up maybe 10-fold faster. But here I didn't fine-tune anything like this. I just use one kind of definition of -1 variable for all these kind of analytical things. Okay. So I think it's really coming from the detail. Yes. From how you choose the -1 variable and how does this sunset look like. I also want to remark that we can use the UT integral to simplify this kind of IBP reduction coefficients. Okay, so I refer to Johan's talk about this very useful integral basis. Okay, this integrals with uniform transcendental weights. So for this example, since okay, this diagram has been analytically calculated. So actually, this UT mass integral basis is already known. So 108 UT integrals, which is the basis. So first, we do the normal basis. So this normal basis is some random pickup. This simple integrals without double propagate. So it's very similar to this kind of basis choice from Kira, from reduce but not file. So if you really want to play with analytics, I don't think it's so important, but actually you can finish in 1 week. So the size is quite big, so it's 2.0 gigabytes. And more importantly, you can see the highest power in the -1 variable. You can find the 1, I think it's 1 numerator, okay. In the coefficient is 35, it's quite huge of this one. But if you have this one, you can definitely convert it to this kind of UT basis. You can see, well, quite shorter, so from 2 to 0.5, something like this. And more importantly, you can see actually it's a huge drop of this power of S, which means suppose you don't want this kind of traditional basis coefficients, then you can directly fit this one. That requires much fewer numerical points to get the analytics. Okay, so
this is for the amplitude or for the mass integral?
Just for this kind of integral reduction coefficient, unphysical things. It's just the integral. I give this integral rank 4. I try to reduce it to the ordinary basis. I get this kind of coefficients.
Still, I don't understand. You get the UT basis, okay?
Yes.
You get the differential equation, so you have some integrals.
Yes. Yes.
So maybe 1,000. And you calculate them, and you get this number.
No, I say I have this 108 UT integrals. Okay.
Sorry, what?
I have this 108, this UT integrals. Then I just randomly pick up this any kind of rank 4, this integral, which is not in the master, which is not in the UT. I try to reduce that to the UT. That's through. Yes, 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 it's the integral. Sorry.
Give us some idea which integral you
took. Rank 4. It's rank 4. Yes, rank 4 simple ones. Yes, I put it there. You use this kind of traditional basis, get quite big, well, the high power, but this one lower power. So I would say that maybe it's a suggestion in the future, if you have this UT basis, then you can use it to get a shorter coefficient. Then of course, I think the main idea is you don't want to really get the analytic IBPs. You really try to do it numerically. Try to make this kind of linear relation as short as possible. So you can do the kind of numerical points as fast as possible. And then you try to fit the amplitude. You don't try to fit this kind of unphysical algebra things. Okay, you may ask about the rank 5 reduction. I apologize, I don't have it right now. It's still on the way. I calculated some cuts, but not all the cuts. I'm sorry, I'm teaching this my first semester. It took almost half of my time, so it's still on the way. Sorry. Okay, so this is a summary. I'm talking about slightly this, on the traditional way. If you have these linear relations, you try to truncate it. Get a smaller linear system by this modeling the section, and if you really want this kind of IBP analytical coefficients, you can do this large scale polarization, this kind of numerical fitting using GPI space to get the coefficient. But I don't say this coefficient is very important because we try to use it numerically. So the main point is I try to make this kind of linear relation as short as possible, so you can do this kind of numerical thing as fast as possible. So you have many numerical points you have to go through. Yes, so I give this talk, so my purpose is not for competition. My point is to try to find the collaboration. It seems that we use this kind of Baikov cut a lot, and we try to study this kind of different vectors for Baikov IBP a lot. So I really try to find something we can collaborate with the intersection theory method. At least to find the relation. So this kind of good directions with this kind of intersection number computation. And another thing is actually it's mentioned already many times, but we still didn't see the detail, is this suppose we try to truncate this kind of IBP relation, not from the momentum space, not from the Baikov space, but suppose we try to do it with a Lee-Pomeranski representation. Then we want to say that for some real examples, then we say how sparse this kind of system is, and if it's very triangular, so you can easily solve it. That's the thing. Okay, so the last thing is this kind of advertisement. Thanks a lot. Sorry.
Very good. So open for questions, Claude.
Okay, so just to make sure I understand. So in the last part, you advocated to solve the IBPs numerically?
Yes.
What do you mean by that? That you, for every kinematic point, you would solve the IBP system numerically?
There are many different ways to do that. I would advertise T-channel parallels package, this finite flow. I think this is a very efficient thing. So this one is really doing everything is a finite field number. Okay, this everything is just a number, and then you run it many times, you try to fit it. What we did is slightly different. We do it semi-numerically. So the thing is we put some of this kind of variables to constant, some of this kind of variables to be symbolic, and then we do this Gaussian elimination. If it can be finished like in 5 hours, then we trust it. Then we try to parallelize it.
Okay, but so you want to get in analytic solutions of the IBPs
via
numerical techniques, or do you really want to run it every kinematic point in your numerical code? Okay.
Yes.
Okay.
Yes.
You but then you will still get an analytic solution of this. So, okay.
Yes, amplitude. Yes, amplitude. Yes.
Even I guess you want to reconstruct the coefficients of the function.
I just show the possibility if you want to construct the IP coefficient, it's not hard, yes.
On the localization trick you mentioned,
Yes.
could you put additional comments on that? I'm quite interested in the speed up technique on that.
Yes, this technique. Yes, yeah. So this technique is if you try to do this kind of algebraic geometry thing with some parameters or Mendelssohn variable and the math. Traditionally you can run it like in this kind of rational function field of these parameters. Then the computer will feel free just to divide by s plus t, this kind of things. But definitely they will slow down the computation. So we find that the correct way to do that is to treat this kind of parameters as your physical variables. Okay, so if you have this kind of byte of z variables or Feynman is some variables, you just treat it equally as this kind of s. Then forbid any kind of pole in s and t or this dimension d like this. Okay, so the trickiest thing here is when you do global basic computation with this kind of equal footing of all these kind of variables, okay, and you run this kind of ordering, you will get a huge system output. Although the computation is very, very fast, but then the generating system is huge, quite redundant. But then the trick is you try to export this result back to this kind of physical ring. Okay, the ring with the rational function field with this kind of s and t. And in that one, you can simply use this kind of leading term criteria to see what kind of generator is really there, which one is redundant. It takes almost no time. So that's a trick.
I just have one small one.
Okay.
So you say that there's an email interface to your code. Is this going to be publicly available?
No. Sorry. There actually there's two parts. So this first part, this kind of module in the section, I think right now this one is quite stable. So I'm going to, with the student, we try to publish a singular program just to say generate this kind of truncated smaller system. But for the second one, this kind of thing, if you really want to get the analytical IBP, this coefficients, then the thing is we use this kind of GPI space to parallelize this kind of thing. But unfortunately, this GPI space is not an open source software. It's really commercial ones. So the second part is not so stable, I have to say, because for this kind of fully analytical computation by numericals, I tuned a lot of things in my computation. It's not so stable yet.
Right. So if there's no more questions, we can thank Yang and all the speakers for the I'll have some comments about it.
Yes, okay. So I have two two comments. So the first is that, as we said in detail, you are all invited to the social dinner at Café Pedrocchi. It's at 8 p.m. and it's 10 meters away from the Christmas tree where we met yesterday. And the second announcement is that for the vegetarian guest, please, before going out, take this red card. This green card. Green card. The green card to put on your table when at your seat, so that the waiters can recognize you. Okay. So before going out, then take your green card. It doesn't work for US, but for tonight it will. So thank you again to all the speakers of the day.